So, here's something worth thinking about as you settle in tonight. Right now, as you lie there, something is passing through your body that nobody on Earth can fully explain. Billions of tiny particles called neutrinos are streaming through you every second, coming from the core of the sun, and physicists still don't agree on some of their most basic properties. You are, at this very moment, a kind of witness to one of the open questions of physics, and you don't have to do anything about it except breathe, and settle in and listen. Let that thought sit with you for a moment. You don't need to understand it yet. You don't need to do anything with it at all. Just notice that it's true, that right now, in the quiet of this room, something is happening inside your own body that the people who have spent their entire lives studying the universe cannot yet fully describe. It's not a problem you need to solve. It's not a test. It's just a quiet fact sitting there alongside you in the dark, like the sound of your own breathing, like the weight of the blanket across your chest. Tonight we're going to go through all of the unsolved problems in physics, from the very beginning of why physics even needed to exist, through the history of how we got so good at explaining the universe, all the way to the strange, honest edges where our best explanations simply stop. By the end, you'll understand not just what these mysteries are, but why they're mysteries, and why the smartest people alive haven't been able to close them yet. This isn't a story about failure. It's a story about how far understanding can go, and where it currently runs out of road. It's a story about the places where the map still has blank spaces, and about the people who have spent centuries drawing that map, carefully, patiently, sometimes getting it wrong, sometimes getting it right, always pushing the edge of what's known just a little further out. If you fall asleep somewhere along the way, that's perfectly fine. That's the point. There's no test at the end of this, no quiz, nothing to remember. The ideas will still be here if you want to come back to them, whether that's in 10 minutes or not at all tonight. Just let your body settle into the mattress, let your breathing slow down, and let the words come to you at whatever pace your mind wants to take them. You can drift in and out, you can let your attention soften. The sound of these words will keep going, a quiet thread you can follow or let go of, whichever feels more restful right now. Let's go back a very long way, further than you might expect. Long before anyone used the word physics, people in ancient Mesopotamia were lying outside at night, much like you are lying in bed right now, and watching the sky move. Around 4,000 years ago, in the region we now call Iraq, Babylonian astronomers kept meticulous records of the positions of planets. They didn't have telescopes, they had their eyes and clay tablets and patience that stretched across generations. Night after night, they looked up and they wrote down what they saw. They noticed that 5 points of light moved differently than the thousands of fixed stars around them. These 5 lights didn't stay in place. They wandered, slowly, across the background of the other stars, tracing out paths that repeated over months and years. The Babylonians called these wandering lights by names that have come down to us across all those centuries as the ancestors of what we now call planets. They didn't know what these objects were made of. They didn't know why they moved the way they did, following those particular paths across the sky rather than some other paths. They had no physics, no mathematics of motion, no understanding of gravity or orbits or the true structure of the solar system. What they had was attention and patience and a willingness to keep looking, night after night, year after year, building the first long-term data set in the history of science. Generations of Babylonian skywatchers passed their clay tablets down, adding to the record, refining the measurements, noting when a particular wandering light appeared in a particular constellation and when it would likely appear there again. They were building something, slowly and carefully, without knowing exactly what they were building, without knowing that 4,000 years later, someone would be lying in a bed, in the dark, talking about their work as the beginning of a story that still hasn't ended. This is worth pausing on, because it tells you something important about physics from the very start. Physics began not with an answer, but with a question that someone was willing to sit with for a very long time. It began with people looking up at the night sky and admitting, to themselves and to each other, that they didn't know what they were seeing, and then deciding to pay attention anyway, to keep watching, to keep recording, to keep the question open rather than closing it too quickly, with a comfortable but incomplete explanation. That posture, that willingness to sit with not knowing, is still at the heart of physics today, and it's part of what makes the unsolved problems we'll talk about tonight not failures, but something more like the leading edge of that same ancient, patient practice of attention. In ancient Greece, a few centuries after the Babylonian astronomers had built their careful records, that same wandering light puzzle caught the attention of philosophers who wanted more than records. They wanted reasons. They wanted explanations. They wanted to understand not just where the planets would appear in the sky, but why they moved at all, what caused their motion, what they were made of, what principles governed their behavior. This was a different kind of attention than the Babylonian approach. It was less about careful measurement and more about building a coherent picture, a system of thought that could explain everything at once. Thales of Miletus, around 600 BCE, proposed that natural events had natural causes, not divine whims, which was a radical idea in a world used to explaining lightning and earthquakes as the moods of gods. If thunder wasn't Zeus being angry, what was it? If the sun didn't cross the sky because a god was pulling it in a chariot, what moved it? Thales didn't have the answers to these questions in a modern sense. He didn't have experiments or equations. But he made a crucial shift in the way people thought, a shift toward the idea that the world operates according to consistent, natural principles that can be understood by human minds, rather than according to the unpredictable will of supernatural beings. That idea, that nature is understandable, that it follows rules we can figure out, is so basic to modern thought that it's easy to forget it had to be invented, that someone had to propose it for the first time, against the grain of everything most people believed. A few generations after Thales, Aristotle built an entire physical system, one where everything in the heavens was made of a perfect, unchanging substance he called ether, moving in perfect circles because circles were considered the most perfect shape. In Aristotle's physics, the world below the moon was the realm of change and decay, where things were born and grew and died and fell apart. But the world above the moon, the heavens, was fundamentally different. It was eternal, unchanging, made of that pure fifth element, ether, and its motions were circular, because circles, having no beginning and no end, were the shape of eternity itself. Everything had its proper place in this system. Heavy things, made of earth and water, fell toward the center of the universe, which was the center of the earth. Light things, made of air and fire, rose upward. The planets and stars, made of ether, moved in their perfect circles around the central earth. And everything made sense. Everything had an explanation. Everything fit. Aristotle's physics dominated Western thought for nearly 2,000 years. It felt complete. It explained falling objects. It explained the motion of the stars. It gave answers to nearly everything people asked. If you dropped a stone, it fell because it was made of earth, and its natural place was at the center. If flames rose, they rose because fire's natural place was at the outer edge of the earthly realm. If the planets circled the earth, they did so because they were made of ether, and circular motion was the only motion appropriate to their perfect nature. The explanations were satisfying. They made intuitive sense. They fit with everyday experience, with the way things felt. And it was, in many important ways, wrong. Objects don't fall the way Aristotle said they do. Heavier objects don't fall faster than lighter ones, in the straightforward way his system implied. The heavens are not made of a separate perfect substance. The moon is made of rock, not aether, and it has craters and mountains, marks of change and imperfection. The earth is not the stationary center of everything. It moves, spinning on its axis and orbiting the sun. But here is the important part for tonight. The part that's easy to miss if you're just keeping score about who was right and who was wrong. Aristotle's physics felt finished to the people who used it. They believed they had explained the universe. For 2,000 years, students learned this system and felt, reasonably, that the big questions had been settled, that what remained was just filling in details, clarifying small points, applying the established principles to particular cases. That feeling, the feeling of having arrived at a complete picture, is one of the most persistent illusions in the history of science, and you'll hear it come up again and again tonight, because it happened more than once. It happened with Aristotle's physics, which felt final for 2 millennia and then turned out to be built on foundations that couldn't hold. It happened with Newton's physics, which felt final for 2 centuries and then turned out to be an approximation, a special case of something deeper. And there's a reasonable chance it's happening right now, in our own time, about problems we don't yet know we're getting wrong, about assumptions we haven't yet thought to question, about cracks in the current picture that are too small to notice yet, waiting for someone to pay attention in just the right way. Around 150 CE, the astronomer Ptolemy in Alexandria took the wandering light puzzle and built an extraordinarily detailed mathematical model to explain it. Ptolemy worked in the great library of Alexandria, with access to centuries of Babylonian records and Greek geometrical knowledge, and he constructed a system of extraordinary complexity and power. In his model, the Earth sat still at the center of everything, and the planets moved in small circles called epicycles, which themselves moved along larger circles called deferents. Each planet traced out a looping, spiraling path through space, a circle riding on a circle, and the combined motion produced the observed patterns in the sky, including the strange backward loops that planets sometimes make, where they seem to pause in their eastward motion and drift westward for a few weeks before resuming their normal direction. Ptolemy's model handled these retrograde motions elegantly, mathematically, with circles upon circles. It was complicated, but it worked. It could predict where the planets would appear in the sky with real accuracy. For over 1,000 years, this model was taught as settled truth. Students didn't question it any more than you might question the numbers on a clock. It was simply how the universe was understood to operate. But the model had a strange, uncomfortable feature. It kept needing more circles. Every few centuries, as measurements got a little more precise, as new observations accumulated, astronomers had to add another small circle to make the predictions match reality, to account for some tiny discrepancy that the previous version of the model couldn't quite capture. The model was accurate, but it wasn't elegant, and more than that, it wasn't quite honest about what was happening. It was patched, again and again, rather than fundamentally correct. Each new epicycle was a small admission that the underlying picture wasn't quite right, even if nobody at the time thought of it in those terms. They were just making the model work, refining it within the accepted framework, never questioning the framework itself. Then, in 1543, a Polish astronomer named Nicolaus Copernicus published a book, quietly, near the end of his life, proposing something that unsettled centuries of certainty. He suggested that the sun, not the earth, sat at the center, and that the earth itself was one of the wandering lights, moving through space just like the other planets. This didn't immediately solve everything. His model still used circles, and it still needed adjustments to match observations precisely, and in fact it wasn't much simpler than Ptolemy's model in terms of the number of circles required. But it removed a layer of unnecessary complexity, and more importantly, it planted a seed. It suggested, quietly but persistently, that the way things had been understood for over 1,000 years might not be the only way to understand them, that the center might be somewhere else entirely, that the Earth might not be as stationary and special as it felt. Later, a German astronomer named Johannes Kepler, working with astonishingly precise data collected by his mentor Tycho Brahe, took the Copernican seed and grew something new from it. Tycho Brahe had spent decades making the most accurate naked-eye astronomical measurements in history before the invention of the telescope, building enormous instruments on his island observatory and recording planetary positions with a precision that nobody had approached before. When Kepler inherited this data after Tycho's death, he spent years trying to fit it to various circular models, and none of them worked. None of them matched the precision of Tycho's observations. And then, after years of struggle, he tried something different. He tried ellipses, slightly flattened ovals, instead of perfect circles. And the numbers snapped into place, almost perfectly, without extra circles bolted on to patch the differences. Kepler discovered that the planets move in ellipses, with the Sun at one focus of the ellipse, and that they speed up when closer to the Sun and slow down when farther away, sweeping out equal areas in equal times. He published these laws in the early 1600s, and for the first time, the numbers matched the sky with a kind of clean precision that didn't require constant patching. This is one of the quiet turning points in the history of understanding, the moment when a description of nature became simpler and more accurate at the same time, rather than one improving only at the cost of the other. Usually, making something more accurate means making it more complicated, adding more details, more corrections, more epicycles. But here, accuracy and simplicity move together, in the same direction, and that convergence is one of the signs that you might be onto something real, something deeper than the model you had before. But notice something about what Kepler had, because this is where the real problem that needed solving starts to take shape. He had a description. He knew how the planets moved, with remarkable precision. He did not know why. Why should a planet slow down and speed up, depending on its distance from the Sun? Why ellipses, and not some other shape? Why did these particular mathematical relationships hold, rather than some other relationships? Kepler himself believed, for a time, that the answer had something to do with mystical harmonies, musical ratios in the structure of the cosmos, the planets singing a kind of silent music as they moved, their speeds and distances corresponding to the intervals of a cosmic scale. He wasn't foolish for thinking this. He simply didn't yet have the tool that would answer the question properly, because that tool hadn't been invented. He had a beautiful, precise description of the pattern, and he had no way to explain the pattern's origin. This is where we'll pause for now, at this moment in the story, with the pattern described but not yet understood, with the how established but the why still hanging open. The same situation, in different forms, will come up again and again as we move forward tonight. Physicists today have extraordinarily precise descriptions of many things: the behavior of particles, the expansion of the universe, the rotation of galaxies, and in some cases, just like Kepler, they are still waiting for the deeper explanation, the tool that hasn't been invented yet, the insight that will make the pattern not just described, but understood. The open questions of physics sit exactly at this boundary, between what we can measure and describe, and what we can actually explain. And that boundary, as you'll hear, is still very much with us, still very much unsettled, still waiting for someone to notice something that everyone else has overlooked, the way Kepler noticed that circles weren't working and tried ellipses instead. But for now, let all of that rest. Let the Babylonians and their clay tablets, the Greeks and their circles, Kepler and his ellipses, let all of them settle quietly into the background. You don't need to hold on to any of it. There's nothing to memorize, nothing to recall. Just let the shape of the story drift past, and let your breathing stay slow, and let the next part come when it comes. The tool arrived, decades later, in the mind of an English scientist named Isaac Newton. In the mid-1660s, when Cambridge University closed due to an outbreak of plague, Newton retreated to his family home in the countryside, and over roughly 2 years, thinking largely alone, he worked out ideas that would reshape how humans understood motion itself. He developed calculus, a new kind of mathematics capable of describing continuously changing quantities, things like speed and acceleration, in a precise way nothing before it could manage. And he proposed something audacious, that the same force pulling an apple to the ground was the exact same force keeping the moon in orbit around the Earth, and the Earth in orbit around the Sun. One universal law of gravitation, applying equally to falling fruit and wandering planets. Take a moment to let that settle. A single rule, simple enough to write on a small piece of paper, governing the fall of a leaf from a tree, and the motion of entire worlds across the vastness of space. This was not a small idea. It was the kind of unification that physicists have been chasing ever since. The dream that underneath the chaos and variety of nature, there might be a few simple principles holding everything together. Newton found one of those principles, and when he finally published this work in 1687 in a book called the Principia, it did something almost no scientific work before it had done. It didn't just describe how planets move, it explained why, using the same simple rule that explained a dropped stone. Kepler's ellipses, those slightly flattened ovals that had taken years of painstaking calculation to fit to Tycho Brahe's data, fell directly out of Newton's mathematics. They weren't a separate observation that had to be fitted in, an extra circle bolted onto a model that kept getting more complicated. They were a natural consequence, something that the equations produced on their own, without being asked, simply because that's how gravity works when one object orbits another. This is worth sitting with for a moment, because it captures something deep about what physics is trying to do. Kepler had a beautiful description. He could tell you how a planet moved, where it would be in the sky on any given night, with a precision that had never been possible before. But he couldn't tell you why it moved that way. He could trace the shape of the orbit, but he couldn't explain what made that shape necessary rather than some other shape. Newton's equations didn't just trace the orbit, they made the orbit inevitable. They showed that if gravity follows an inverse square law, if the pull between two objects weakens with the square of the distance between them, then the paths of planets simply must be ellipses, parabolas, or hyperbolas, the family of curves called conic sections. There was no need to assume circles, no need to add epicycles, no need to patch the model with extra complications. The simplicity at the heart of the law produced the complexity of the observed motion without any extra effort at all. For about 200 years afterward, Newtonian physics felt, once again, like a complete and closed system. The same feeling that had settled over Aristotle's physics for 2 millennia, the sense that the big questions had been answered and what remained was just filling in details, returned with new confidence. Scientists used Newton's equations to predict eclipses years in advance, to calculate the paths of comets, to design bridges and machines. The laws of motion and gravity turned out to be useful far beyond astronomy. Engineers could calculate the stresses on a beam, the trajectory of a cannonball, the flow of water through a pipe, all using the same basic principles that governed the planets. It seemed, for a long and fruitful stretch of time, that the universe had finally given up its deepest secrets and that the human mind, armed with calculus and the laws of motion, could figure out anything it set its attention on. Then came a moment that felt like final proof. In the 1840s, astronomers noticed something odd about the orbit of Uranus. The planet wasn't quite following the path that Newton's equations predicted. There were small, persistent wobbles, tiny deviations from the expected orbit, that couldn't be explained by any known object in the solar system. A generation earlier, this kind of discrepancy might have been written off as a measurement error, or a limitation of the instruments, or one of those small mysteries that nature keeps to itself. But the confidence in Newtonian physics had grown so strong, so thoroughly tested and confirmed across so many different domains, that the astronomers took a different approach. They assumed, reasonably and boldly, that the equations were right and that something unseen was causing the wobble. They ran Newton's equations backward. Instead of starting with a known mass and calculating its motion, they started with the observed motion and calculated where a previously unknown mass would have to be to cause it. They predicted, with pencil and paper and the mathematics of gravity, the existence of a planet no one had ever seen. In 1846, astronomers pointed a telescope to the exact predicted location and found Neptune sitting there, almost exactly where the mathematics said it should be. You can imagine the feeling in that moment, the quiet confirmation that the universe really did operate like a vast, predictable mechanism, that human reason could reach out across millions of miles of empty space and touch something invisible, name it, locate it, and then see it with their own eyes. This was an enormous triumph. Not a military victory or a political achievement, but something quieter and more lasting. The demonstration that the laws of physics were not just useful approximations, but genuine maps of reality, reliable enough to lead you to a world you had never seen. That confidence, that sense of near completion, is important to hold on to for a moment, because it's about to be tested, gently at first, and then very seriously. The pattern you heard about earlier, the one where a system of thought feels finished right before a crack appears, was about to repeat itself. Newtonian physics, at the height of its explanatory power, with Neptune as its fresh and glowing proof, was about to encounter problems it could not solve, problems hiding in small, technical discrepancies that most people would never notice, the kind of tiny anomalies that only show up when you're measuring something with extraordinary care and precision. The first crack appeared in the exact same place Newton's gravity had just triumphed: planetary orbits. Mercury, the innermost planet, the one closest to the Sun, has an orbit that doesn't stay perfectly still in space. The entire elliptical path slowly rotates over time. Imagine drawing an oval on a piece of paper, and then very slowly turning the paper so that the oval's long axis points in a slightly different direction than it did before. That rotation, that gradual turning of the entire orbit, is called precession, and it happens to all the planets to some degree. Most of it is caused by the gravitational tugging of the other planets, each one pulling gently on Mercury and slowly shifting the orientation of its path around the Sun. Astronomers calculated how much this rotation should be, based on the gravitational pull of all the other planets, using Newton's equations, the same equations that had found Neptune hiding in the dark. When they compared the prediction to actual observations, there was a tiny discrepancy: a few dozen extra arcseconds per century. To give you a sense of how small this is, an arcsecond is 1/3600th of a degree, a sliver of angle so narrow that it's hard to picture. The extra rotation was a few dozen of those slivers, spread out over 100 years of planetary motion, an amount so small it's almost absurd to care about, except that Newton's physics had predicted planetary positions with remarkable precision everywhere else. Every other planet's orbit made sense, matched the equations, behaved the way it should, but Mercury's orbit, and only Mercury's orbit, had this stubborn extra rotation that refused to go away, no matter how carefully the calculations were checked and rechecked. Astronomers assumed, reasonably, that there must be another undiscovered planet, closer to the Sun, tugging at Mercury the way the unseen Neptune had tugged at Uranus. The logic was sound, and it had just worked, spectacularly, a few decades earlier. If an unexplained wobble meant a hidden planet once, maybe it meant a hidden planet again. They even gave this hypothetical planet a name: Vulcan, after the Roman god of fire, appropriate for something orbiting so close to the Sun's heat. And they searched for it, carefully, for decades. Some observers even reported seeing it: small dark spots passing across the face of the Sun that might have been a previously unknown world. But those sightings never held up under closer scrutiny. The transits of Vulcan were never confirmed, never repeated consistently, never photographed. The planet was never found, because it didn't exist. The discrepancy wasn't caused by a missing object pulling on Mercury from the darkness. It was caused by something wrong, in a small but real way, with Newton's entire picture of gravity itself. The equations that had found Neptune, that had explained the fall of an apple and the motion of the moon and the paths of comets, were not exactly wrong. They were almost perfectly right, right enough to take you to an unseen planet, right enough to build bridges and predict eclipses. But they were not completely right, and the tiny discrepancy in Mercury's orbit was the quiet, persistent signal that something deeper was going on, something that Newton's laws couldn't quite capture. This is how cracks in physics often appear, not as loud, dramatic failures, but as small, stubborn numbers that don't add up, measurements that are just barely off, anomalies that a less careful science might ignore or explain away. The precession of Mercury's orbit was a whisper of trouble, a faint warning that the complete and closed system wasn't quite as complete as it seemed. The second crack appeared somewhere completely different, in a part of physics that seemed, on the surface, to have nothing to do with planets or gravity or the motion of celestial bodies. It appeared in the physics of light and heat, in a problem that seemed small and technical and deeply unglamorous, and it would end up cracking open the entire foundation of physics in ways that are still being sorted out tonight. In the late 1800s, physicists were trying to understand something called black body radiation. The name sounds technical, but the phenomenon itself is completely ordinary, something you've seen many times. A black body is just an idealized object that absorbs all the light that hits it and then radiates energy back out, based purely on its temperature. Real objects approximate this behavior well enough. The coils of an electric stove, the filament of an old-fashioned light bulb, the walls of a kiln. As an object gets hotter, it glows, first a dull red, then orange, then white-hot, shifting through colors as its temperature rises. The color you see is just the peak of a whole spectrum of radiation that the object is giving off, some visible, some infrared, some ultraviolet, spread across a range of wavelengths. Physicists wanted to predict exactly how much energy a hot object should radiate at each wavelength, to go from knowing the temperature of the object to knowing the full curve of its glow. Using the established, well-tested physics of the time, treating light as a continuous wave, they set up the equations and solved them. The calculation worked beautifully for longer wavelengths, for the red and infrared parts of the spectrum. The predictions matched real measurements almost exactly. But at shorter wavelengths, in the ultraviolet and beyond, the calculation broke down. Not just a little off, not a tiny discrepancy like Mercury's orbit, but catastrophically, absurdly wrong. The equations predicted that any hot object, any object at all with a temperature above absolute zero, should emit infinite energy in the ultraviolet range. Infinite energy, blasting out of every surface, every wall, every lamp, every human body, a flood of ultraviolet radiation that would instantly vaporize everything in existence. Objects don't do this. You are not currently being blasted with infinite ultraviolet energy from your lamp or your walls or your own skin. The prediction was absurd, and everyone knew it was absurd, and yet the mathematics, built on physics that worked perfectly everywhere else, insisted on it. It became known, half-jokingly, as the ultraviolet catastrophe, a small, technical-sounding problem about the glow of hot objects, a discrepancy in a corner of physics that most people never thought about at all, and the equations were producing nonsense. Not a small error that could be patched with an extra correction term, but an infinite, screaming impossibility that told physicists something fundamental was wrong with their understanding of light and energy. This is another pattern worth noticing, because it comes up over and over in the history of physics. The old physics, the physics that felt complete and closed, didn't fail in some obscure, esoteric domain accessible only to a few specialists. It failed trying to explain something as ordinary as why a heated piece of metal glows red and not ultraviolet. The deepest revolutions in physics have often started with the most mundane phenomena, with something you can see in your own kitchen, with a puzzle that a child might notice if they were paying close enough attention. The ultraviolet catastrophe was that kind of puzzle, ordinary, specific, and completely inexplicable within the existing framework. The fix came from a German physicist named Max Planck in 1900, and it was a fix he didn't fully believe in at first. Planck was not a revolutionary by temperament. He was a careful, conservative physicist who respected the established theories and wanted to understand why they were breaking down in this particular case. He tried everything he could think of to make the equations work, without changing the underlying assumptions about light. Nothing worked. Finally, almost in desperation, he tried something that seemed physically unreasonable. He assumed that light energy could only be emitted in small, discrete packets, rather than as a smooth, continuous wave. In the continuous picture, energy could be divided up infinitely, smaller and smaller without limit, and that infinite divisibility was part of what led to the infinite ultraviolet prediction. But if energy came in tiny, indivisible chunks, if there was a smallest possible unit of light at each frequency, the mathematics changed completely, and the terrifying infinite prediction simply disappeared. Planck called these packets quanta, from the Latin word for how much, and he treated the idea mostly as a useful mathematical trick, a formal device that made the equations work without necessarily describing something real. He was uncomfortable with the implications for years. The idea that energy was grainy, that it came in discrete pieces rather than flowing smoothly, contradicted centuries of physical intuition, and Planck kept hoping someone would find a more conventional explanation that didn't require this strange quantization. But 5 years later, in 1905, a young patent clerk in Switzerland named Albert Einstein took Planck's idea seriously as physical truth, not just a mathematical convenience. He used it to explain another stubborn puzzle called the photoelectric effect, where light striking a metal surface knocks electrons loose, but only if the light is above a certain frequency, no matter how bright it is. Shine a dim blue light on the metal, and electrons come off. Shine an intense red light, no matter how bright, and nothing happens. This detail made no sense if light was purely a wave, because a wave's energy depends on its brightness, its amplitude, and a bright red light should have more than enough energy to knock electrons loose, even if a dim blue light could do it. But if light came in discrete particle-like packets, later called photons, each with an energy determined by its frequency, the puzzle resolved itself. A blue photon carries enough energy to kick out an electron. A red photon, no matter how many of them you send, each one individually lacks the energy needed. Einstein's explanation, small and precise, would eventually earn him the Nobel Prize, and it planted quantum mechanics firmly into physical reality, not just as mathematical bookkeeping, but as a genuine feature of how the world works at its smallest scales. That same year, 1905, sometimes called Einstein's miracle year, he also published his special theory of relativity. This was a separate line of thinking, growing out of a different set of problems in physics, problems about the nature of light and motion that had been troubling physicists since the late 1800s. Special relativity showed that space and time are not separate, fixed backdrops the universe happens inside of, but are woven together into a single fabric, and that measurements of time and distance depend on how fast you're moving relative to something else. A clock moving past you ticks slower than a clock sitting still beside you. A ruler moving past you is shorter than the same ruler at rest. These are not illusions or limitations of measurement. They are genuine features of space and time themselves, built into the geometry of the universe, and they become noticeable only at speeds close to the speed of light, which is why our everyday experience never reveals them. A decade later, in 1915, Einstein extended this into general relativity, a new theory of gravity that went beyond Newton in a fundamental way. Newton had imagined gravity as a force that reaches out across space, a kind of invisible string pulling objects toward each other. Einstein proposed something different. He described gravity not as a force at all, but as the shape of space and time themselves, curved by the presence of mass. Picture a heavy bowl placed on a stretched sheet. The sheet dips, creating a curved depression around the bowl. If you roll a smaller marble nearby, its path bends not because the ball is pulling on it directly, but because the surface it's rolling on is curved. That's the central image of general relativity. Mass tells space how to curve, and curved space tells objects how to move. When Einstein applied his new equations to that old, small, stubborn discrepancy in Mercury's orbit, the one that had sent astronomers hunting for an invisible planet named Vulcan for half a century, something quietly remarkable happened. His equations predicted the extra wobble exactly, without needing any new planet at all. The tiny discrepancy that Newton's gravity couldn't account for, the 43 arcseconds per century that had resisted every attempt at explanation within the old framework, fell out of general relativity naturally, a consequence of the sun's mass curving space in its immediate vicinity more sharply than Newton's simpler picture had accounted for. Mercury, being the closest planet to the sun, felt that extra curvature the most, and its orbit shifted accordingly. The mystery wasn't a hidden object, it was a hidden flaw in how gravity itself had been understood, a flaw too small to matter for most purposes, but measurable with careful instruments and patient observation. Newton's physics was not wrong, exactly. It was an excellent approximation that broke down under strong gravity and high speed, a special, simpler case of something deeper. You can still use Newton's equations to send a rocket to the moon, to calculate the trajectory of a baseball, to design a bridge. They work perfectly well for almost everything you encounter in daily life. But they are not the final story. They are a chapter in a longer book, and Einstein wrote the next chapter, showing that space and time themselves are dynamic, flexible, responsive to the presence of matter in ways that Newton never imagined. You can rest here for a moment. Let your eyes close now if they aren't already. You don't need to follow every word from here. Just let it wash over you, the sound of it, the shape of the ideas moving past. The explanation continues either way, and there's nothing to catch up on, nothing you need to hold on to. It will still make sense whenever you tune back in, the way a story does when you drift in and out of sleep, catching fragments that still manage to hold together. The planets are still out there, moving in their ellipses, curving through space shaped by the sun's mass. The photons are still behaving like particles when they hit a metal surface, and like waves when they pass through a narrow gap. The universe is still doing what it does, whether you're tracking every detail or not, and there's something restful in that, something that doesn't ask anything of you at all. By the 1920s, physics had two extraordinarily successful new frameworks. General relativity described the very large, gravity, the bending of space and time, the motion of stars and galaxies, with a precision that still feels almost uncanny. Quantum mechanics, developed by a group of young physicists including Werner Heisenberg, Erwin Schrödinger, Niels Bohr, and Paul Dirac, described the very small, atoms, electrons, and light, with equally precise results. Both frameworks passed every experimental test thrown at them. They made predictions that were verified again and again, in different laboratories by different teams, using different methods, and each time the numbers came back matching what the equations said they should be. And yet, despite all that success, despite decades of confirmation and practical application, the two theories didn't agree with each other. They didn't fit together. They described the same universe using rules that couldn't both be true at the same time. General relativity treats space and time as smooth and continuous, like a stretched fabric with no gaps, no grain, no smallest unit. You can zoom in indefinitely, and space stays smooth, the same way a mathematical curve has no pixels when you magnify it. Quantum mechanics, on the other hand, treats energy and matter as fundamentally grainy, made of discrete packets, with genuine randomness built into its core. Energy doesn't flow like water from a tap. It comes in lumps, quanta, and those lumps behave in ways that are fundamentally uncertain, not just unknown to us, but genuinely undetermined, until something interacts with them. When physicists tried to combine the two frameworks, to write equations that described gravity using quantum rules, the mathematics broke down. It produced nonsensical, infinite answers, much like the old ultraviolet catastrophe had done for the physics of hot objects a few decades earlier. This tension between general relativity and quantum mechanics is not a minor footnote, not a small technical issue that only specialists worry about. It sits at the very center of physics today, and it is the source of some of the deepest unsolved problems we'll spend time with tonight. Let's slow down here and actually sit with what these two theories say, in plain language, because everything that follows depends on holding both pictures gently in mind at once. Not memorizing them, not mastering the details, just getting comfortable with the basic shape of each, the way you might get comfortable with the layout of a familiar room in low light. Picture space, the space around your bed, the space between you and the ceiling. Picture it not as empty nothing, not as a void with objects floating in it, but as something with a texture, something that can stretch, compress, and curve. The way a mattress dips slightly under your own weight right now, that gentle indentation where your body meets the surface, that's not a bad way to think about what general relativity says space does in the presence of mass. Any object with mass, a planet, a star, your own body lying there in the dark, curves the space around it. The heavier the object, the deeper the curve. And other objects moving through that curved space follow paths that look, from a distance, like they're being pulled by a force. But there is no force in the traditional sense. There is only geometry, only the shape of space itself guiding things along. The Earth doesn't orbit the Sun because the Sun reaches out across 93 million miles of empty space and grabs it with an invisible hand. The Earth orbits the Sun because the Sun, being massive, curves the space around itself, and the Earth is simply moving in the straightest possible line through that curved space. A straight line through curved geometry looks like a curve to an observer who thinks the geometry should be flat. It's the same reason a marble rolling across a dipped trampoline curves its path without anything pulling on it directly. The marble is going straight as it can, but the surface it's rolling on isn't flat, so its straight path bends. This is the central insight of general relativity, and it's a picture that has been tested with extraordinary precision over the past century. It correctly predicts the bending of starlight around the Sun, first confirmed during a solar eclipse in 1919, when astronomers photographed stars near the Sun's edge and found them slightly shifted from their usual positions, their light bent by the Sun's gravitational curve. It correctly predicts the existence of black holes, regions where space curves so extremely, so deeply, that nothing, not even light, can climb back out once it crosses a certain boundary. It correctly predicts gravitational waves, ripples in the fabric of space itself, caused by violent events like colliding black holes, waves that travel across the universe at the speed of light, stretching and squeezing everything they pass through by amounts smaller than the width of an atom, first directly detected in 2015, a full century after Einstein predicted them. The theory works. It describes the large-scale structure of reality with a precision that has never been matched by any competing idea. Now picture the other framework, quantum mechanics, which governs the world of atoms and particles, the very small. And here, the picture is completely different. In this world, things don't have definite properties until they're measured. An electron doesn't have one exact location the way a marble does, sitting at a particular point in space with a particular speed. Before you look, before any measurement happens, the electron exists as a spread-out possibility, a wave of probability, smeared across a range of possible positions and speeds, all at once. It's not that we don't know where it is and are waiting to find out. It genuinely doesn't have a single, definite location until something interacts with it and forces it to take one. And when that interaction happens, when a measurement occurs, the electron settles into one specific place, one specific outcome, chosen at random according to precise probabilities encoded in the mathematics of the wave function. This isn't a statement about our ignorance, about not yet knowing the details. It appears, as far as every experiment has ever shown, to be a genuine feature of reality itself. The universe, at its smallest scales, doesn't seem to run on fixed, predetermined tracks the way a clockwork does. It runs on probability. You can set up two completely identical experiments with identical starting conditions and get two different outcomes, not because you failed to control some hidden variable, but because the fundamental physics only gives you odds, not certainties. This was deeply uncomfortable for many physicists when it was first understood, and it remains philosophically strange today. But the mathematics works, and the experiments confirm it every time. There's another feature of quantum mechanics that's worth sitting with, because it's so strange that even Einstein, who helped lay the foundations for the theory, never fully accepted it. Two particles can become linked, or entangled, in such a way that measuring one instantly tells you something about the other, no matter how far apart they are. If you entangle two particles and then separate them, sending one to a laboratory in New York and the other to a laboratory in Tokyo, and then measure the first one, the second one's state is determined instantly, faster than light could travel between the two locations. Einstein called this spooky action at a distance, and he thought it pointed to something incomplete in the quantum picture, some hidden variables that would restore locality and common sense. But experiment after experiment, over decades, has confirmed that entanglement is real, that the correlations between entangled particles really do appear instantaneously, and that no hidden local variables can explain the results. The universe, at this level, is simply non-local, connected in ways that don't map onto our everyday intuitions about space and separation. So here you have two pictures, both extraordinarily well tested, both making predictions that match reality with precision that can seem almost unreasonable. General relativity gives you a smooth, continuous universe, where gravity is geometry, where space bends and time stretches, where cause and effect move at the speed of light, through a fabric that has no smallest piece. Quantum mechanics gives you a grainy, probabilistic universe, where energy comes in lumps, where particles don't have definite positions until measured, where two things can be entangled across any distance. Both pictures are true, in the sense that both produce correct predictions in their own domains. And both cannot be simultaneously literally true in their current forms, because they describe the basic nature of space, time, and cause and effect in ways that contradict each other. This is the deepest, oldest, unsolved problem sitting underneath modern physics. It's usually called the problem of quantum gravity, and it can be stated simply: nobody has yet found a way to describe gravity, the curving of space and time, using the same probabilistic, grainy rules that govern everything else in the universe. Every time someone tries to write down equations that treat gravity as a quantum force, the way electromagnetism and the nuclear forces have been treated, the mathematics produces infinities that can't be removed, predictions that make no physical sense. The smoothness of general relativity and the graininess of quantum mechanics refuse to fit together, and until they do, our understanding of reality has a seam running right through its middle. There have been serious attempts to stitch this seam closed. One major approach, probably the most famous, is called string theory. The central idea of string theory is that the smallest building blocks of reality aren't point-like particles at all. Instead of imagining an electron as a tiny dot with no internal structure, string theory imagines it as a tiny vibrating string of energy, a loop or a segment, far too small to ever directly observe. To give you a sense of the scale, a proton, itself already almost unimaginably tiny, is billions of times larger than the strings of string theory. Different vibration patterns of these strings, in this framework, correspond to different particles, the same way different vibration patterns on a guitar string produce different musical notes. One pattern of vibration looks like an electron, another looks like a photon, another looks like a quark, and so on through the whole particle zoo. And one particular vibration pattern, one note in this cosmic music, has the properties of a graviton, the hypothetical quantum particle that would carry the force of gravity. This is part of why string theory has attracted so much attention. It seems to naturally include gravity as part of its structure, unlike other approaches that have to add gravity in by hand. String theory has an appealing mathematical elegance. The equations are deep and rich and have led to genuine insights in pure mathematics, connections between areas of study that had seemed completely unrelated. But it also has features that make it difficult to test. It requires extra dimensions of space beyond the 3 we experience, 6 or 7 additional dimensions, curled up so tightly that we'd never notice them in daily life. These extra dimensions are needed for the mathematics to work out consistently, for the strings to have enough room to vibrate in all the ways that produce the particles we observe. And despite decades of intense work by some of the most capable physicists alive, string theory has not yet made a testable prediction that distinguishes it clearly from other ideas, one that current or near-future experiments could actually check. It's a framework of great mathematical depth, and it may turn out to be right, but as of tonight we don't know. A different approach, called loop quantum gravity, tries something else entirely. Instead of adding extra dimensions, it starts with general relativity and tries to quantize space itself. The central proposal is that space is not smooth and continuous, the way it feels to you lying in bed right now, but is actually made of tiny, discrete loops and networks, a fine-grained fabric with the smallest possible size. Just as matter comes in atoms and energy comes in quanta, space itself, in this view, comes in tiny, indivisible units. There is a smallest possible distance, a smallest possible area, a smallest possible volume, much smaller than an atom, below which the concept of distance stops meaning anything at all. Space is grainy, quantized, the same way energy turned out to be grainy when Planck and Einstein worked it out over a century ago. Loop quantum gravity makes some interesting predictions, particularly about what might have happened at the very beginning of the universe, suggesting that the Big Bang might have been a big bounce, a transition from a previous contracting phase rather than a true beginning from a point of infinite density. But like string theory, it hasn't yet produced a prediction that current experiments can test and confirm. There are other approaches too, less famous, but seriously pursued by dedicated groups of physicists. Ideas involving causal sets, where space-time is built from a web of cause and effect relationships rather than smooth geometry, a vast network of discrete events linked by which ones can influence which others. Ideas involving asymptotic safety, which try to tame the mathematical infinities directly, using more careful versions of the existing quantum equations, showing that gravity might be perfectly well behaved at high energies after all, just in a more subtle way than the simpler attempts assumed. None of them, as of tonight, has won. None of them has been confirmed by experiment. This is the honest state of one of the biggest open questions in physics. We have two extraordinarily accurate descriptions of reality, each passing every test we can devise, and we do not yet have one description that contains them both. Let's move now to a different kind of mystery, one that isn't about combining theories, but about a piece of the universe we can measure the effects of, but cannot directly see or identify. This is a shift in focus, from the very small to the very large, from the laws that govern individual particles to the stuff that fills the space between galaxies. And it begins with an observation made in the early 1930s by a Swiss astronomer named Fritz Zwicky. Zwicky was studying a cluster of galaxies called the Coma Cluster, a rich grouping of hundreds of galaxies bound together by their mutual gravity. He was measuring how fast individual galaxies within the cluster were moving, using the Doppler shift of their light to determine their speeds along our line of sight. When he calculated how much mass the cluster needed to have to hold those fast-moving galaxies together, to keep them from flying apart into the surrounding void, the number he got was startling. It was far larger than what he could account for by adding up all the visible stars, all the glowing gas, all the ordinary matter that he could see with his telescopes, roughly 10 times larger. The cluster needed to contain far more mass than all its visible material could provide, or else, by the well-tested laws of gravity, it should have scattered long ago. Zwicky proposed there must be some invisible material, mass that doesn't shine, doesn't glow, doesn't interact with light at all, but still exerts a gravitational pull, still curves space the way any mass does. He called it dunkle Materie, dark matter. At the time, in the 1930s, most scientists treated this as an odd anomaly, perhaps a measurement error or an overestimate of the galaxy speeds, and largely set it aside. Zwicky had a reputation for being difficult and abrasive, and his colleagues may not have been inclined to take his most dramatic claims at face value. The dark matter idea sat on the shelf for decades, a curious footnote that nobody quite knew what to do with. The problem refused to stay quiet, though. In the 1970s, an American astronomer named Vera Rubin, working with a new, more precise spectrograph that could measure the rotation of spiral galaxies in fine detail, found something that shouldn't have been possible under standard gravity. In our own solar system, planets farther from the Sun orbit more slowly. Mercury zips around in just 88 days, while Neptune takes 165 years. This is exactly what Newton's equations predict, because the sun's gravitational pull weakens with distance, and an object farther out needs less speed to stay in its orbit. Rubin expected the same pattern in galaxies. Stars near the busy, mass-dense center should orbit fast. Stars out in the sparse, mostly empty outer regions, where the visible matter thins out, should orbit slowly, the way distant planets do. Instead, she found something completely different. The stars far out at the edges of galaxies were moving just as fast as stars near the center, sometimes faster. The rotation curve, the graph of orbital speed versus distance from the center, didn't drop off the way it should. It stayed flat. This is called a flat rotation curve, and under the laws of gravity as understood, it simply shouldn't happen. Unless there's a huge amount of unseen mass spread throughout and around each galaxy in a roughly spherical halo, extending far beyond the visible edge of stars, providing the extra gravitational pull needed to keep those outer stars moving at their observed speeds. Vera Rubin's data, carefully gathered and meticulously checked, brought dark matter back from obscurity and made it one of the central puzzles of modern astrophysics. Since Rubin's work, evidence for this invisible mass has piled up from many independent directions, which is part of why physicists take it seriously rather than dismissing it as a fluke or a measurement artifact. Gravitational lensing provides one of the most direct lines of evidence. When light from a distant galaxy passes near a massive foreground object, like a galaxy cluster, the mass of the cluster bends the path of the light, the way a lens bends light in a pair of glasses. This is a direct prediction of general relativity, and it's been observed many times. The amount of bending tells you how much mass is in the foreground cluster, and time after time, the bending is far greater than the visible stars and gas alone could cause. There's extra mass there, curving space more than the visible matter can explain. Detailed maps of the cosmic microwave background, the faint afterglow of radiation left over from roughly 380,000 years after the Big Bang, tell the same story. The tiny temperature variations in this ancient light, variations of just a few parts in 100,000, form a pattern that depends on how much matter of different kinds existed in the early universe. The pattern can only be explained if roughly 5 times more matter exists than the ordinary matter making up stars, planets, and the elements in your own body. Even the way galaxies clustered together as the universe aged, forming the vast cosmic web of filaments and voids we observe today, only matches computer simulations if that extra invisible mass is included from the start. If you run a simulation with only ordinary matter, you get a universe that looks nothing like ours. Add dark matter, and the large-scale structure emerges, naturally and in detail. So the evidence that something is out there, gravitationally, is about as solid as evidence gets in astrophysics. Multiple independent lines of inquiry, each relying on different physical principles, all pointing to the same conclusion. What that something actually is remains genuinely unknown. It doesn't emit light, absorb light, or reflect light, which is why it's called dark, though transparent might honestly be a more accurate word. It isn't made of the same particles that make up you, your bed, the air in your room. It isn't ordinary matter, built from protons, neutrons, and electrons, because if it were, it would interact with light the way ordinary matter does, and we would see it, or at least see its shadow against background sources. The leading guess for decades was a category of particles called WIMPs, weakly interacting massive particles, hypothetical particles that would feel gravity but almost nothing else, passing through ordinary matter as easily as neutrinos do, maybe even more easily. Enormous, sensitive detectors have been built deep underground, shielded from cosmic radiation, in old mines in places like South Dakota and Italy, waiting in the dark for a dark matter particle to occasionally, once in a great while, bump into an ordinary atom and produce a faint signal. As of tonight, decades into this search, no such signal has been definitively found. The detectors sit there, quiet, patient, and empty. Other candidates are still being explored. A much lighter theoretical particle, called the axion, so light it would behave more like a wave than a particle, might be the answer. Dedicated experiments are searching for axions using strong magnetic fields and ultra-sensitive microwave cavities, looking for the faint signal of an axion converting into a photon. There are even more exotic ideas, including the possibility that gravity itself behaves slightly differently than Einstein and Newton described at very large scales, meaning there might be no dark matter particle at all, just an incomplete theory of gravity, a gap in our understanding, rather than a missing substance. That alternative, called modified Newtonian dynamics or MOND, explains some galaxy observations well, particularly the flat rotation curves that Vera Rubin first measured. But it struggles badly with other observations, particularly the behavior of galaxy cluster collisions, where the visible matter and the gravitational center clearly separate, the kind of observation that a modified gravity theory finds hard to accommodate. This is why most physicists still favor the idea of an actual unseen particle. But favor is not proof. Either way, roughly 85% of the matter in the universe remains, tonight, unidentified. Not a minor component, not a trace element, but the vast majority of the material stuff of reality, unknown in its fundamental nature. You can let that sit with you for a moment, or you can let it drift past. The dark matter will still be there, unseen and quiet, whether you hold on to the thought or let it go. Now let's sit with something even stranger, something found more recently, in the late 1990s. Two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were studying a particular kind of exploding star called a Type 1 Lea supernova. These are not ordinary stars quietly burning through their fuel over billions of years. They are violent final events, the death of a certain kind of dense stellar remnant called a white dwarf, and they have a useful property. They reliably release almost exactly the same amount of energy every time they detonate. The physics of the explosion is consistent enough that each one shines with roughly the same true brightness, what astronomers call a standard candle. If you know how bright something really is, and you measure how bright it looks from Earth, you can calculate how far away it must be, the same way you can estimate the distance of a car at night by how dim its headlights appear, assuming all headlights have roughly the same true brightness. Both teams were using these supernovae to measure something specific. They wanted to know how much the expansion of the universe was slowing down over time. The expansion itself had been known since the late 1920s, when an American astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, measured the distances and speeds of distant galaxies and found a clear pattern. The farther away a galaxy was, the faster it was receding from us. The universe was not static, not fixed in place, but growing, stretching, with space itself expanding between the galaxies. This was already a profound shift in how humans understood the cosmos, but it raised a natural question. Gravity pulls things together. All the mass in the universe, all the galaxies and stars and dark matter, should be pulling on each other, acting like a brake on the expansion, slowing it down gradually over cosmic time. The question was, how much? Was the expansion slowing quickly, meaning the universe might eventually stop and collapse back on itself? Was it slowing just enough to coast to a halt in the infinite future? Measuring the rate of this deceleration was the goal, and the supernovae, those distant standard candles, were the tool. What the two teams found instead, published in 1998, upended expectations entirely. The expansion of the universe isn't slowing down, it's speeding up. The most distant supernovae were dimmer than they should have been if the expansion had been decelerating as expected. They were farther away, which meant the universe had stretched more than any model, with only matter and gravity, could account for. Distant galaxies are receding from us faster and faster as time goes on, as though some kind of repulsive pressure is winning out over gravity's inward pull, on the largest scales imaginable. Not a small effect at the edges of measurement, not a subtle correction to an otherwise correct picture. A complete reversal of what almost everyone expected, confirmed by two independent teams using different telescopes and different analysis methods, so it couldn't be dismissed as an instrument artifact or a statistical fluke. Physicists gave this unknown repulsive influence a name: dark energy. The name is a placeholder, a label for something we can measure the effects of, but cannot yet describe in terms of a deeper physical cause. And current best measurements suggest it makes up roughly 68% of all the energy and mass in the universe, dwarfing both dark matter and ordinary matter combined. Let that number settle for a moment. Dark matter, that invisible stuff holding galaxies together, makes up about 27%. Ordinary matter, everything you can see and touch, every star and planet and cloud of gas, every grain of dust and every living cell, makes up roughly 5%. Dark energy makes up the rest, more than 2/3 of everything that exists, and we have no confirmed explanation for what it actually is. This is a humbling fact, and it's worth sitting with rather than rushing past. Everything familiar to you, everything you can see, touch, weigh, and study directly, the stars, the planets, your own body, the air in the room, the blanket over your chest, adds up to something like 5% of what actually exists. The remaining 95% is dark matter and dark energy, two separate mysteries, both confirmed through overwhelming indirect evidence, neither one understood at a fundamental level. The universe you experience, the world of light and solid objects and measurable warmth, is a thin layer floating on an ocean of something else, something invisible and unidentified, something that neither emits light nor absorbs it, something that pushes the cosmos apart, even as gravity tries to pull it together. This is not a metaphor. It is the current best description of reality, backed by decades of careful measurement, and it leaves most of reality unexplained. The leading explanation for dark energy treats it as a property of empty space itself. In this view, space is not just a passive backdrop, a stage on which the events of the universe play out. Space has its own energy, its own persistent pressure, and that pressure pushes outward, stretching space further apart. The more space there is, the more of this energy there is, so the effect doesn't dilute as the universe expands. It stays constant, or nearly constant, which is why it can drive an acceleration that gravity cannot overcome. Physicists call this the cosmological constant, and the idea has an interesting history. Einstein originally introduced it into his equations of general relativity in 1917, for entirely different reasons. At the time, most astronomers believed the universe was static, eternal, and unchanging, and Einstein's equations, in their original form, predicted that a universe full of matter should either expand or contract under its own gravity. To keep the universe still, he added a term, a constant, a kind of repulsive energy that would perfectly balance gravity's pull and hold everything in place. When Hubble's observations later showed that the universe was actually expanding, Einstein reportedly called the cosmological constant his biggest blunder, an unnecessary complication that had kept him from predicting the expansion before it was observed. And then, decades after his death, the cosmological constant turned out to possibly be necessary after all, just not for the reason he'd first imagined, not to hold the universe static, but to explain why it's speeding up. Sometimes an idea in physics gets shelved, not because it's wrong, but because it answers a question that hasn't been asked yet. And when the question finally arrives, the old idea is there waiting, dusty but intact. But there's a problem with this explanation, and it's a severe one. In quantum mechanics, empty space isn't truly empty. Even a perfect vacuum, with no particles, no radiation, no matter of any kind, is still seething with activity at the quantum level. Brief, fleeting fluctuations, particles and their antiparticles winking into existence and then annihilating each other almost instantly, borrowed from the energy of the vacuum itself, existing just long enough to satisfy the uncertainty principle before disappearing again. This isn't theoretical speculation. The effects of these vacuum fluctuations have been measured in laboratories, in the tiny forces they exert between closely spaced metal plates, a phenomenon called the Casimir effect. Empty space has energy, real and measurable, and that energy should, according to general relativity, act like a cosmological constant, contributing to the expansion of the universe. Physicists tried calculating how much energy this quantum activity in empty space should produce, hoping the number might match the observed strength of dark energy. The calculated number came out wrong. Not slightly wrong, not off by a factor of 2 or 10 or even 1,000. It came out wrong by roughly a factor of 10 followed by 120 zeros. That's a number so large it has no meaningful name. A prediction so wildly off from observation that it's sometimes called the worst prediction in the history of physics. If the quantum vacuum energy were as large as the simplest calculation suggests, the universe would have ripped itself apart in the first fraction of a second after the Big Bang, expanding so violently that no structure, no galaxies, no stars, no planets would ever have had a chance to form. That gap between what quantum theory predicts empty space should weigh and what astronomers actually observe is called the cosmological constant problem, and it remains one of the most severe unresolved tensions between our two great frameworks of physics. Something is canceling out the vacuum energy almost perfectly, leaving behind just a tiny residue, the dark energy we observe, or the calculation is missing something fundamental, or empty space doesn't behave the way we think it does at cosmic scales. Whatever the resolution, it's not a small detail. It's a chasm in our understanding, a place where the two most successful theories in the history of science give answers that differ by more than 100 orders of magnitude, and nobody knows how to close the gap. Let's turn now to a mystery closer to the beginning of everything, one that concerns not what fills the universe today, but why there's a universe of matter at all, rather than nothing. This is not a poetic or philosophical question about why anything exists instead of nothingness. It's a specific, technical puzzle with numbers attached, and it goes like this. According to the physics developed over the past century, when the universe was born in the event we call the Big Bang, nearly 14 billion years ago, the enormous energy present in those first fractions of a second should have produced matter and antimatter in exactly equal amounts. Antimatter is a real, laboratory-confirmed substance, first predicted mathematically by the physicist Paul Dirac in 1928, and detected experimentally just 4 years later. Every particle of ordinary matter has an antimatter twin, identical in mass but opposite in electric charge. The electron has the positron, the proton has the antiproton. They are mirror images, and when a particle meets its antimatter twin, both instantly annihilate, converting entirely into pure energy. A flash of light, a burst of gamma rays, and then nothing of either remains. If the early universe truly created matter and antimatter in perfectly equal amounts, as the equations suggest it should have, then as the universe cooled and expanded, nearly all of that matter and antimatter should have found each other and annihilated completely. Particle meeting antiparticle, pair after pair after pair, until almost nothing was left. The universe would be filled with nothing but light, an expanding sea of photons cooling as space stretched, and no matter at all. No stars, no planets, no galaxies, no you, lying in your bed, breathing quietly in the dark. Obviously, that isn't what happened. You exist. The fact that you are listening to these words means that the annihilation was not complete. Stars exist. There's an enormous amount of ordinary matter in the universe, whole galaxies full of it, and vanishingly little naturally occurring antimatter anywhere we've looked. Something, in those first moments, tipped the balance ever so slightly in favor of matter. For roughly every billion particle-antiparticle pairs that annihilated back into pure energy, one lone particle of matter was left over, without a partner to annihilate with. One survivor in a billion. That tiny leftover, that 1 in a billion asymmetry, is everything. Everything you see around you, everything in the observable universe, every star and planet and cloud of gas, every living thing that has ever existed, is made from that tiny leftover imbalance. The entire visible universe is a rounding error, a slight excess in matter's favor, from a process that should have been perfectly symmetric. Physicists call this puzzle baryon asymmetry, And the honest, unresolved question is simple to state and brutally hard to answer. Why did that asymmetry exist at all? What caused matter to be produced just slightly more often than antimatter in the early universe? And why was the asymmetry exactly the size it was, 1 part in a billion, rather than some other number, rather than 0, rather than large enough to produce a completely different universe? There are candidate explanations. Certain particle interactions, first observed experimentally in the 1960s by physicists James Cronin and Val Fitch, show that some physical processes very slightly favor matter over antimatter. This property is called CP violation, and it proves, at least, that nature isn't perfectly symmetric between matter and antimatter. The symmetry is broken, if only by a tiny amount. This is a necessary ingredient for any explanation of why matter won out. If the laws of physics treated matter and antimatter exactly the same in every respect, then no imbalance could ever arise, and the early universe would have annihilated itself completely. CP violation shows that the door is open, that an asymmetry is possible in principle, but the amount of CP violation observed so far in known particle interactions is far too small, by many orders of magnitude, to account for the actual imbalance we see in the universe. The asymmetry we can measure in the laboratory, in the behavior of certain rare particle decays, is not nearly enough to explain why 1 particle in a billion survived the early universe. Something is producing more of this asymmetry than physicists currently know how to explain, somewhere in physics not yet fully mapped out. There may be new particles, new forces, new interactions that only show up at energies far higher than our current accelerators can reach. The answers, if they exist, are buried in the first moments of the universe, in conditions so extreme that our current theories strain to describe them. You may have drifted a little just now, and that's fine. There's nothing urgent here, nothing you need to hold on to tightly. Let your breathing stay slow. The explanation keeps going gently, whether you're catching every word or just the shape of it, the way music continues, even when your attention wanders from the notes. The matter in your body, the carbon and oxygen and calcium and iron, all of it is still there, still holding together, still made from that ancient 1 in a billion excess. That fact doesn't change whether you're following the details or not. Let's stay with particles a while longer, moving to a puzzle involving one of the strangest members of the particle family, the neutrino. We began tonight with neutrinos, those billions of tiny particles passing through your body every second from the core of the sun, and now we'll spend a little more time with them, because they sit at the center of several connected open questions. Neutrinos are, in a very real sense, everywhere. They're produced by nuclear reactions in the sun's core, by radioactive decay inside the Earth, by exploding stars across the galaxy, even by the Big Bang itself, leaving behind a faint cosmic neutrino background that still fills the universe today, a relic as old as the cosmic microwave background, but far harder to detect. They are almost unbelievably abundant, the most numerous particles of matter in the universe after photons of light, and they are almost unbelievably difficult to catch. They interact with ordinary matter so weakly that trillions of them pass through your entire body every single second of your life, right now, without a single one, on average, bumping into a single atom inside you. A neutrino could pass through a wall of lead, a light year thick, with a decent chance of emerging on the other side, without having interacted with anything at all. Detecting them at all requires enormous instruments, tanks holding thousands of tons of ultra-pure water or other sensitive material, buried deep underground in old mines or under mountains, shielded from cosmic rays and other interfering particles, patiently waiting for the extraordinarily rare moment when a neutrino does interact with something and produces a faint flash of light that can be recorded and studied. For decades, physicists assumed neutrinos, like photons of light, had no mass at all. They were treated as massless particles in the Standard Model, zipping through space at the speed of light, weightless and eternal. Then, starting in the late 1990s, experiments studying neutrinos produced by the sun and by cosmic rays hitting the upper atmosphere found something that didn't fit that picture. Neutrinos come in three types, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And physicists found that neutrinos can spontaneously change from one flavor into another as they travel, a phenomenon called neutrino oscillation. A neutrino that starts out as an electron neutrino might, by the time it reaches a detector, have transformed into a muon neutrino or a tau neutrino, and then possibly back again. This oscillation, this shifting of identity mid-flight, is only possible, according to the underlying quantum mathematics, if neutrinos have some tiny amount of mass. A massless particle travels at the speed of light, and for a massless particle, time does not pass. If time does not pass, no change can occur. The fact that neutrinos change at all means they must experience time, which means they must be traveling slightly slower than light, which means they must have mass. The earlier assumption that they were massless turned out to be simply wrong. This realization earned a Nobel Prize in 2015, and it was genuinely important, but it also opened a door to a set of questions still unanswered tonight. Physicists know neutrinos have mass, but they don't know how much. The experiments that detected oscillations can measure the differences between the masses, but not the absolute values themselves. All we know is that neutrino masses are astonishingly small, less than a millionth the mass of an electron, which is itself already one of the lightest known particles. Why are they so light? Why are neutrino masses so dramatically smaller than every other particle in the Standard Model? There's no explanation within the current framework. It's just a fact sitting there, waiting for a deeper theory to make sense of it. They don't know the exact order of the three neutrino masses, a puzzle called the mass hierarchy problem. It's possible that two of the neutrinos are relatively light and one is heavier, or that one is light and two are heavier. The experiments haven't yet been able to distinguish between these two possibilities, and the answer matters for how neutrinos fit into the larger picture of particle physics. And they don't yet know whether neutrinos might be their own antiparticles. Most particles have distinct antiparticle partners. The electron and the positron are different. The proton and the antiproton are different. But it's theoretically possible, for electrically neutral particles, that a particle could be its own antiparticle, identical to itself in every way. This special possibility is called a Majorana particle, and if neutrinos are Majorana particles, it could have deep implications. It could help explain that earlier mystery of matter-antimatter asymmetry we just talked about, connecting these two open questions together in a way physicists find deeply suggestive but haven't yet proven. If neutrinos are their own antiparticles, certain very rare nuclear decays should be possible, and experiments are currently searching for those decays in deep underground laboratories, waiting for a signal that might take years to appear, if it appears at all. There's a related puzzle, sometimes discussed alongside these neutrino questions, called the hierarchy problem, though it concerns a completely different kind of imbalance. This one is about the strength of the fundamental forces of nature. There are four known fundamental forces: gravity, which holds you to the Earth and holds the Earth in orbit around the Sun; electromagnetism, which governs light and electricity and the structure of atoms; and two forces that operate only inside the atomic nucleus, called the strong and weak nuclear forces. The strong force binds protons and neutrons together, holding the nucleus tight against the electromagnetic repulsion of all those positive charges packed into a tiny space. The weak force governs certain kinds of radioactive decay, the slow transformation of one kind of particle into another. Gravity, compared to the other three, is almost incomprehensibly weak. You can test this yourself in a strange, small way. A tiny refrigerator magnet, something you can hold between two fingers, is able to overcome the gravitational pull of the entire planet Earth to hold a piece of paper against your fridge door. The whole mass of the Earth, all 6 septillion kilograms of it, pulling down on that paper with the full strength of its gravity, and a small magnet, drawing power from the electromagnetic force, beats it easily. Gravity is weaker than electromagnetism by a factor of roughly 10,000 trillion. That number is so large it resists intuition. It means gravity is 40 orders of magnitude feebler than the other fundamental forces, a gap so vast it seems to demand an explanation. The hierarchy problem asks why this is. Why is gravity so dramatically weaker than everything else? It's not just a matter of curiosity. The weakness of gravity is connected to another question. Why is the mass of the Higgs boson, the particle that gives other particles their mass, as light as it is? If you calculate how heavy the Higgs should be, taking into account the quantum fluctuations that should add to its mass, you get a number that is enormously larger than what was actually measured at the Large Hadron Collider. Something is canceling out those contributions, keeping the Higgs light, and whatever is doing that cancellation might also explain gravity's weakness. Physicists have proposed several ideas, including theories involving extra hidden dimensions of space where gravity might leak away and dilute, spreading its strength across more dimensions than we experience. And theories involving a symmetry called supersymmetry, which predicts a heavier partner particle for every known particle, partners whose quantum contributions would naturally cancel out the problematic ones. Sensitive experiments at the Large Hadron Collider have searched carefully for these predicted supersymmetric partner particles for well over a decade. None have been found so far, which has left this once-favored explanation looking considerably less certain than it did 15 years ago, and left the hierarchy problem sitting there, unresolved, tonight. Let your attention soften again if it needs to. These puzzles aren't going anywhere. They've been waiting for decades, some of them for a century, and they can wait a little longer while you rest. Gravity is still holding you gently to the bed, still the weakest force and yet the one that shapes the cosmos, still unexplained in its faintness. The neutrinos are still passing through you, weightless or nearly so, silent and invisible, and everywhere, carrying with them questions that don't yet have answers. None of that requires anything from you right now. You can just lie there, breathing, letting the words come and go. Let's shift now to a mystery you can actually observe directly, one hiding in your own daily experience, something so familiar you may never have thought to question it: the arrow of time. Not time as a concept, not the measurement of seconds and minutes and hours, but something more basic. The fact that time has a direction, the fact that it flows one way and not the other. This is so woven into the fabric of being alive that it hardly seems like a puzzle at all. Of course time moves forward. Of course the past is behind us and the future ahead. Of course you remember what you did yesterday, but not what you'll do tomorrow. These feel like statements about the nature of existence so obvious they barely need saying. But the fundamental equations of physics, nearly all of them, from Newton's laws of motion to Einstein's relativity to the equations of quantum mechanics, work equally well running forward or backward in time. This is a deeply strange fact, and it's worth letting settle for a moment. If you filmed two billiard balls colliding on a smooth table and played the footage in reverse, the reversed footage would still perfectly obey the laws of physics. Every force, every transfer of momentum, every angle of deflection would be consistent with the same equations. Nothing in the underlying mathematics says time has to flow in only one direction. The laws that govern the smallest interactions of matter are, in this sense, time-symmetric. They don't know about past and future. They don't distinguish between the two directions. And yet, your entire lived experience says otherwise, powerfully and completely. You remember yesterday, not tomorrow. You can decide what to eat for breakfast in the morning, but you cannot decide what you ate last week. An egg breaks and scrambles in a hot pan, the proteins unwinding and tangling, the clear white turning opaque, the yellow yolk spreading and solidifying. A scrambled egg never, not once in the history of the universe, spontaneously reassembles itself into a whole egg, sitting neatly in its shell, the proteins folding back up, the yolk pulling itself together, the shell fragments flying up from the floor and fusing seamlessly around the restored contents. Ice cubes melt in a warm room, the ordered crystal structure dissolving into liquid water, the neat cubes slumping into puddles. Puddles of water don't spontaneously freeze into ice cubes on a warm countertop, extracting heat from the air and organizing themselves into perfect lattices. Something is clearly making time move in one direction only, at the level of everyday experience, even though the fundamental equations underneath don't require it. Something is imposing an arrow on time, a forward direction, a distinction between past and future that the basic laws of physics don't contain. The best current explanation for this involves a concept from a branch of physics called thermodynamics, and specifically something called entropy. Entropy is, loosely speaking, a measure of disorder. More precisely, it's a measure of how many different microscopic arrangements could produce the same overall large-scale appearance, the same macroscopic state. Think about a neatly organized deck of cards, sorted by suit and rank, all the hearts together in order, all the spades, all the diamonds, all the clubs. There is only one arrangement, one specific ordering of the 52 cards, that looks like that. That's low entropy. There are very few ways to be that ordered. Now think about a shuffled deck. Almost every possible ordering of 52 cards looks shuffled, looks random, looks disordered. The number of arrangements that look shuffled is vastly larger than the number that looks sorted. That's high entropy. Disorder is simply more probable than order, not because of any force pushing things toward messiness, but because there are so many more ways to be messy than to be neat. The second law of thermodynamics states that, in any closed system, entropy tends to increase over time. It doesn't have to increase in every moment, at every location. There can be small, local decreases in entropy, little pockets of increasing order, like a refrigerator cooling its interior, or a seed growing into a tree. But overall, on average, across the whole system, disorder increases. This isn't a law in the sense of a decree handed down by some authority. It's a statistical observation, a statement about overwhelming probability. Disordered arrangements vastly outnumber ordered ones, so random processes drift naturally toward disorder, the same way shuffling cards tends to make a sorted deck messier, essentially never neater, purely as a matter of overwhelming statistical odds. It's not impossible for a shuffled deck to accidentally sort itself if you shuffle long enough. It's just so monumentally unlikely that you could shuffle from now until the end of the universe and never see it happen even once. This explains, reasonably well, why time seems to flow in one direction in daily life. Things move from unlikely, ordered states toward likely, disordered states. Eggs scramble but don't unscramble. Ice melts but doesn't unfreeze in a warm room. Perfume sprayed in one corner of a room spreads out to fill the whole space but never gathers itself back into the bottle. We experience that drift, that movement from order to disorder, from less probable to more probable arrangements, as the forward flow of time. The arrow of time, in this view, is the arrow of increasing entropy. The future is simply the direction in which entropy is higher. The past is the direction in which it was lower. But this explanation pushes the real mystery back a step further, rather than fully resolving it. If entropy naturally increases, if systems drift from order to disorder as a matter of statistical near certainty, then entropy must have been extremely low at the beginning of the universe. Extraordinarily ordered, highly unlikely. Because if it had been high at the start, if the universe had begun in a state of maximum disorder, there would be nowhere for entropy to go. No increase would be possible. No arrow of time would emerge. The universe would simply sit, static and unchanging, in a state of complete thermodynamic equilibrium, and nothing like stars or galaxies or life could ever form. So the early universe, right after the Big Bang, must have been in a state of astonishingly low entropy, not just a little bit ordered, not just tidier than average, but ordered to a degree that almost defies description, a state so statistically improbable that it makes a shuffled deck sorting itself look mundane by comparison. Physicists don't have a settled, agreed-upon explanation for why the early universe started in such a low entropy, highly ordered state in the first place. This is sometimes called the past hypothesis, The assumption that the universe began in a very special, very ordered condition, an assumption that the second law of thermodynamics requires but doesn't explain. Explaining exactly why the past hypothesis holds, why the universe began so ordered rather than in some other, far more probable configuration, remains a genuinely open problem. It's connected in complicated ways to ideas about the very structure of the Big Bang itself, to what happened in those first fractions of a second, and to what, if anything, came before it, a question physics currently has no reliable way of answering. Let's turn to another mystery, one located firmly inside the strange rules of quantum mechanics itself. This one is called the measurement problem, and it's worth explaining slowly and carefully because it sits at the philosophical heart of physics, at the place where the mathematics stops and the questions about what's actually real begin. Recall from earlier that in quantum mechanics, particles don't have definite properties until they're measured. Before measurement, an electron exists in something called a superposition, a mathematical combination of multiple possible states at once. It's not that the electron is in one particular place and we just don't know which one. It's that the electron, as described by the theory, is genuinely spread out across multiple possible locations, multiple possible speeds, multiple possible states, all coexisting in the mathematics of the wave function. The wave function is the mathematical object that encodes all the possibilities, all the probabilities, all the potential outcomes, and the wave function itself evolves smoothly and predictably over time, following an equation written down by Erwin Schrödinger in 1926. That smooth evolution is completely deterministic. There's no randomness in it at all. If you know the wave function at one moment, you can calculate exactly what it will be at any future moment. It just spreads and shifts and ripples according to precise mathematical rules. But the moment a measurement happens, the moment someone looks or a detector registers something, or any interaction occurs that extracts information from the system, the wave function appears to do something completely different. It appears to instantly collapse. The smooth spread of possibilities vanishes, and only one specific outcome remains, one definite position, one definite speed, one definite state, and which outcome you get is random. Not random in the sense of being complicated or hard to predict. Genuinely random, according to the theory, with probabilities set by the shape of the wave function just before the collapse. The smooth, deterministic, predictable evolution of the wave function is, in that instant, seemingly abandoned, replaced by a sudden, discontinuous jump to a single result. The strange, unresolved question is this: what exactly counts as a measurement, and why does it cause this collapse at all? The Schrödinger equation, the one that governs the smooth evolution of the wave function, doesn't have a collapse built into it. The collapse has to be added by hand, as a separate rule, a separate postulate, with no clear explanation of when it applies or what triggers it. Is a measuring device special somehow? Does the collapse happen when a particle interacts with a macroscopic object, something large enough to count as a measuring apparatus? Does it require a conscious observer, a mind looking at the result, as some early interpretations, including ones favored for a time by Niels Bohr and others in the 1920s, seem to suggest, or at least didn't rule out? Or is there no real collapse at all? That last possibility is the many worlds interpretation, formalized in 1957 by a physicist named Hugh Everett. In this view, there is no collapse. The wave function never jumps. The smooth, deterministic evolution continues forever, for everything. When a measurement happens, the measuring device doesn't cause a collapse. It becomes entangled with the particle being measured, and the superposition simply grows to include the device, and then the observer, and then the entire laboratory, and then everything else. Every possible outcome actually happens, each one splitting off into its own separate, equally real branch of reality. The version of you hearing these words is experiencing only one branch among countlessly many, a branch where the particular random outcomes of every quantum event in your past happen to fall in the particular sequence that led to this moment. In other branches, other things happened. Other versions of you made different choices, saw different results, lived different lives. All equally real, all equally present, just causally separated, unable to interact with each other after the split. Physicists have proposed several different interpretations over the past century, each mathematically consistent with every experiment ever performed, and yet describing completely different underlying realities. The Copenhagen interpretation, historically the most commonly taught, takes a pragmatic approach. It treats the wave function as a tool for calculating probabilities, a way to predict the statistics of measurement outcomes, without committing strongly to what's happening in reality between measurements. It divides the world into the quantum system being measured and the classical measuring apparatus, and it doesn't try to explain how or why the transition between the two happens. The many worlds interpretation says nothing ever truly collapses, and every possibility genuinely unfolds somewhere, in some branch of a constantly splitting universe. A theory called pilot wave theory, developed by Louis de Broglie in the 1920s and revived by David Bohm in the 1950s, proposes that particles do have definite positions at all times, even when they're not being measured, and that they're guided invisibly by an underlying wave, the wave function, which pushes them along deterministic paths. There's no collapse in this picture either, and no fundamental randomness, just a deeper layer of reality that we don't have direct access to. A newer family of ideas called objective collapse theories propose that wave functions really do physically collapse on their own, spontaneously, at random but very rare moments, without needing a measurement or an observer to trigger it. The odds of a spontaneous collapse increase for larger objects, which is part of why you don't see large everyday objects, tables, cups, sleeping bodies, existing in noticeable superpositions. An electron might stay in a superposition for eons, but a cat-sized object would collapse almost instantly, resolving into a single definite state. Here's the genuinely strange part. The part that makes this an unsolved problem rather than a solved one with several competing translations. Every one of these interpretations makes the exact same testable predictions for every experiment performed so far. There is, currently, no known experiment that could tell you which one, if any, correctly describes what's actually happening in reality. They all agree on what you should see in the laboratory. They all agree on the numbers. They all use the same mathematical formalism to calculate those numbers. They differ only on what the mathematics means, on what's happening behind the scenes, on what reality is actually doing when nobody's looking. Physicists have been arguing about this for roughly 100 years, not because they can't do the mathematics. The mathematics works extraordinarily well and lets us build lasers, transistors, and quantum computers, technologies that depend on quantum effects being real and predictable. The argument persists because the mathematics doesn't, by itself, tell us what's actually real underneath the equations. It gives us a procedure for calculating outcomes, but it doesn't tell us what kind of universe we're living in, whether it's a universe of many worlds, or hidden particles, or spontaneous collapses, or something else entirely. Being unable to answer that question, despite having a theory of extraordinary precision and power, is uncomfortable in a very particular, very human way. By now you may have drifted in and out a few times, and that's exactly right. There's nothing to catch up on. Everything has been settling quietly, whether you were following closely or not. The way sound settles into a room, the way warmth settles into blankets. You can keep resting exactly like this. The arrow of time is still pointing forward, whether you're tracking it or not. The wave functions of the atoms in your body are still doing whatever wave functions do, evolving smoothly or collapsing or splitting into branches, depending on which interpretation you prefer, none of which changes the fact that you're lying there, breathing, your body heavy and warm against the mattress. The measurement problem has been open for a century, and it will still be open when you wake up, if you wake up, if you drift off entirely before this sentence finishes. There's no urgency here, just the quiet presence of questions that don't yet have answers, waiting patiently in the dark. Let's gather some of the smaller, stranger threads now, the ones physicists sometimes call anomalies. These are small, persistent gaps between prediction and observation, places where the numbers don't quite line up, where something measured in the laboratory doesn't match what the equations say it should be. Any one of these might turn out to be a minor error, a subtle miscalibration, a statistical fluke that disappears when more data comes in. Or any one of them might turn out to be the crack that leads to the next revolution, the way Mercury's tiny orbital wobble once did, the way the ultraviolet catastrophe once did. These anomalies are the places where physicists are paying the closest attention right now, because that's often where the new physics hides, in the small discrepancies, in the numbers that refuse to settle. One such puzzle is called the proton radius puzzle. The proton is the positively charged particle sitting at the center of every atom. It's one of the building blocks of ordinary matter, discovered over a century ago, studied intensively ever since. You might think, reasonably, that by now physicists would know how big a proton is, and they do, roughly. The proton has a physical size, a radius, a distance from its center to its edge, although edge is a tricky word for a quantum object that doesn't have a hard surface the way a billiard ball does. Physicists have measured this size two different ways, using two different methods, and for a while those methods gave two different answers. The first method uses ordinary hydrogen atoms, the simplest atom there is, just one electron orbiting one proton. By measuring the energy levels of the electron very precisely, physicists can infer the size of the proton at the center. This method had been refined over decades and gave a consistent number. The second method uses a more exotic version of hydrogen, where the electron is replaced with a heavier particle called a muon. The muon is like an electron in every way, except it's about 200 times heavier, and because it's heavier, it orbits much closer to the proton. Being closer, it's more sensitive to the proton's exact size, and in theory, this should give a more precise measurement. In 2010, when researchers finally performed this muonic hydrogen measurement with enough precision, the proton came out smaller than the standard method had found, by about 4%. 4% doesn't sound like much. It sounds like the kind of difference that could be written off as measurement uncertainty. But both methods were precise enough that 4% was far outside the margin of error. The two numbers disagreed, and neither error bar overlapped with the other. For a while, nobody knew which number was right, or whether some unknown physics was causing the discrepancy. Something about the muon's interaction with the proton that wasn't accounted for in the standard calculations. Years of repeated experiments have mostly narrowed this gap. More measurements, more careful analysis, more cross-checking between different laboratories, and much of the discrepancy now appears resolved in favor of the smaller measurement, the one from muonic hydrogen. The proton is slightly smaller than we used to think, and the old measurements probably had subtle systematic errors that nobody had caught. The underlying episode, even if it's mostly settled now, remains a useful reminder. It reminds us that something as basic as the size of a proton, one of the most familiar particles in existence, the stable core of every atom, can still contain small surprises. It reminds us that precision matters, that measuring something more carefully can reveal cracks in what we thought we knew, even about things we've been studying for 100 years. Another anomaly, one that's still very much alive and unresolved, is called the muon G-2 anomaly. It concerns the same particle, the muon, the heavier cousin of the electron. Muons have a property that makes them behave, in a certain sense, like tiny spinning magnets. They have a magnetic moment, a built-in magnetism that comes from their quantum mechanical nature. When you place a muon inside a strong magnetic field, its spin axis doesn't stay fixed. It wobbles or precesses the way a spinning top wobbles as it slows down, tracing out a slow circle with its axis. The rate of this wobble is determined by the muon's magnetic properties and by the influence of everything around it, every particle and force that interacts with the muon, even briefly, even virtually, through the quantum fluctuations of empty space. Physicists can calculate, using the full mathematical machinery of particle physics, the Standard Model, exactly how fast this wobble should be. The calculation is one of the most precise in all of science. involving contributions from every known particle and force, including subtle quantum corrections that are fiendishly difficult to compute. And they can measure it, using a large experiment that sends muons circling around a specially built 50-foot-wide superconducting magnetic ring, tracking their spins with exquisite precision. The experiments, first at Brookhaven National Laboratory in the early 2000s, and more recently and more precisely at Fermi Lab near Chicago, have found a wobble that is very slightly different from the predicted value. The difference is tiny, a matter of parts per billion, but the measurement is precise enough that the gap appears statistically significant. It looks like it might be real, not just random noise. And if it's real, it suggests something fascinating, something not yet included in the standard model. Some undiscovered particle or force might be subtly influencing the muon's behavior, adding a tiny extra contribution to its wobble that the equations don't account for. A new particle, too heavy to have been produced directly in any experiment so far, could still make its presence felt through these quantum corrections, through its influence on the virtual processes that surround the muon. This is how new physics often first appears, not as a dramatic new particle leaping out of a detector, but as a small, persistent discrepancy in a very precisely measured number, a number that refuses to match the prediction no matter how carefully both are checked. As of the most recent results, the theoretical prediction itself is still being refined and debated by different calculation groups. There's a particular contribution from the strong nuclear force that's exceptionally hard to compute, and different methods give slightly different answers. So physicists are being careful, appropriately careful, about declaring anything settled. The anomaly might still turn out to be a calculation problem rather than a new particle, but if the anomaly holds up under further scrutiny, if the measurement and the prediction both solidify and the gap remains, it could be the first solid experimental crack pointing toward genuinely new physics beyond everything currently known. Something beyond dark matter, beyond the puzzles we've already covered tonight. An entirely new piece of the picture, a new particle or force that nobody has yet named. There's also a persistent set of questions clustered around the standard model of particle physics itself. The standard model is the enormously successful theory developed through the mid to late 20th century that describes all known fundamental particles and 3 of the 4 fundamental forces. It covers electromagnetism, the strong nuclear force, and the weak nuclear force, leaving only gravity out. It has been tested to extraordinary precision over decades in laboratories all around the world, and it has passed every test. Its final missing piece, a particle called the Higgs boson, was finally detected in 2012 at the Large Hadron Collider, the enormous particle accelerator beneath the border of France and Switzerland, after a search lasting nearly 50 years. The Higgs is the particle responsible for giving other particles their mass, or more precisely, the Higgs field that fills all of space interacts with particles and gives them inertia, and detecting the particle was the confirmation that the field really exists, that the mechanism works the way theorists had proposed back in the 1960s. This was a genuine triumph, closing out decades of prediction with direct confirmation. The standard model, as a set of equations and predictions, works nearly perfectly. And yet, physicists broadly agree the standard model cannot be the final, complete story. This isn't a guess or a hope. It's a conclusion based on several separate reasons woven through everything we've already discussed tonight. The standard model has no explanation for dark matter. Whatever particle makes up 85% of the matter in the universe isn't in the model. The standard model has no explanation for dark energy. The accelerating expansion of the universe is completely outside its scope. The standard model, in its original form, assumed neutrinos were massless, and they're not. It has no explanation for why neutrino masses are so tiny, or why they exist at all. The standard model has no explanation for the matter-antimatter imbalance. The amount of CP violation it contains is far too small to account for why we exist, and the standard model has no way at all to include gravity. The 4th fundamental force is simply not part of the framework. It's an extraordinarily accurate map of a large piece of reality, but everyone studying it, including the physicists who helped build it, agrees the map has real, acknowledged blank spaces at its edges. It's a map that works beautifully for the territory it covers, but the territory is only part of the whole. There's one more piece worth adding here, a puzzle that sits quietly next to the matter-antimatter asymmetry we talked about earlier. It's called the strong CP problem, and it's a little more technical than some of the others, but it points to something genuinely strange about the universe. Recall that physicists observed, back in the 1960s, that some particle interactions very slightly favor matter over antimatter. This broken symmetry is called CP violation, and it's a necessary ingredient in explaining why any matter survived the early universe at all. The symmetry isn't perfect. Matter and antimatter aren't exact mirror images in every respect. The laws of physics have a tiny preference, and that preference, over billions of years and countless particle interactions, accumulated into the universe of stars and planets and living things we see tonight. Here's the strange twist. The mathematics describing the strong nuclear force, the force that binds protons and neutrons together inside the atomic nucleus, actually allows for a much larger amount of this same kind of symmetry breaking than what's observed in nature. There's a parameter in the equations, a number that could, in principle, be anything. It could be large, it could produce measurable CP violation in the strong force, effects that would show up in experiments, effects like the neutron having a slightly uneven, egg-like distribution of electric charge rather than being perfectly round. But every precise experiment ever run, including exquisitely sensitive measurements of the neutron's shape, measurements so sensitive they could detect a deviation smaller than a billionth of a meter, finds a number consistent with zero. No asymmetry, no CP violation in the strong force. The neutron is round, perfectly round to the limits of our instruments. The parameter that should be there, that the mathematics allows to be there, is instead set to zero, or so close to zero that we can't tell the difference. A theory doesn't need to work out this way. The equations would be perfectly happy with a much larger value. There's no known reason, no deep principle embedded in the standard model, forcing that particular number to be so close to zero. It's just there, a fact about the universe, unexplained and seemingly fine-tuned. Physicists call this unexplained near-perfect cancellation the strong CP problem, and it's been sitting there, quietly, since the 1970s, waiting for an explanation. One of the most popular proposed solutions involves a new hypothetical particle called the axion. The axion was first proposed in 1977 by physicists Roberto Peccei and Helen Quinn, and it's a strange particle by any measure. It would be extraordinarily light, far lighter than even the neutrino, and it would interact with ordinary matter so weakly that it would pass through entire planets without leaving a trace. If axions exist, they would naturally suppress the CP violation in the strong force, explaining why the neutron is so perfectly round. And here's where the puzzles start to connect. The axion, if it exists, is also a very good candidate for dark matter, a particle that light and that weakly interacting, produced in enormous numbers in the early universe, would behave exactly the way dark matter needs to behave. It would clump together under gravity, forming halos around galaxies, but it would never form stars or emit light or interact in any detectable way except through its gravitational pull. The axion, this hypothetical particle invented to solve one obscure problem, might also solve the much larger problem of what most of the matter in the universe actually is. Two separate unsolved problems in physics, potentially resolved by the same particle. This is part of why so much careful attention is being paid to the search. Dedicated experiments are running right now in shielded laboratories around the world, using strong magnetic fields and ultra-sensitive microwave cavities to try to catch an axion converting into a photon, a single faint flash of light that would announce the existence of a particle that could explain two mysteries at once. Related to this is a much older question, one that has quietly outlasted nearly every other prediction in the standard model. It concerns the proton itself, the humble particle sitting in the nucleus of every atom in your body, the stable core of all ordinary matter. The question is whether the proton is truly, permanently stable, or whether it might, over an almost incomprehensibly long span of time, eventually decay into lighter particles. The Standard Model, as it's currently built, predicts the proton should be exactly stable, forever. There's a symmetry built into the model, a conservation law, that prevents the proton from decaying. If the proton were to decay, it would violate that symmetry, and the model, as it stands, doesn't allow it. But several proposed extensions to the Standard Model, including a family of ideas called Grand Unified Theories, make a different prediction. Grand Unified Theories attempt to show that the three forces described by the Standard Model, electromagnetism and the strong and weak nuclear forces, are really just three different faces of one single unified force, a force that existed in the earliest moments after the Big Bang, when the universe was hot enough and dense enough that the distinctions between the forces hadn't yet emerged. As the universe cooled, this single force separated, or broke symmetry, into the three forces we observe today, the way water can exist as ice, liquid, or vapor depending on the temperature. In these theories, the proton is not perfectly stable. It can decay, just exceptionally rarely. The predicted lifetime is staggering. On average, a proton would decay once every 10, followed by roughly 34 years. That's a number so large it's hard to hold in your mind. The current age of the universe is about 14 billion years, a 1 followed by 10 zeros. The predicted proton lifetime is trillions of times longer than that. No single proton would ever be expected to decay in the lifetime of anyone who has ever lived, or in the lifetime of any star that will ever burn, or in any span of time that has any familiar reference point. But if you gather enough protons together in one place, and you watch them patiently enough, the odds shift. A large tank of water, like the ones used in neutrino detectors, contains an astronomical number of protons. All those protons, sitting there quietly, day after day, year after year. If each one has even a vanishingly small chance of decaying in any given year, the sheer number of them means you might, if you watch long enough, catch one in the act. Deep underground detectors like Super Kamiokande in Japan, a vast tank of ultra-pure water lined with sensitive light detectors, buried under a mountain to shield it from cosmic rays, have spent decades patiently watching. Waiting for a flash of light that would signal a proton inside the water had spontaneously come apart, decaying into lighter particles that would streak through the water and leave telltale patterns. None has ever been observed. Not one confirmed proton decay in decades of watching. This non-observation has already ruled out several specific versions of grand unified theories, the simplest and most elegant ones, the ones that made the clearest predictions. The field has narrowed, but the underlying question hasn't been settled. Whether the proton is truly eternal, or simply extraordinarily patient, remains an open question, and the detectors keep watching, deep underground, in the dark. Let's also spend a little time with the idea of extra dimensions, which comes up in more than one corner of unsolved physics. You experience 3 dimensions of space, up and down, left and right, forward and back, plus 1 dimension of time, which you experience as the forward flow of moments. That's 4 dimensions total in the fabric of space-time, and they seem, in ordinary life, to be all there is. You can't point in a direction that isn't one of those 3. You can't move in a way that takes you outside of them. But several serious theoretical frameworks, including string theory mentioned earlier, require additional spatial dimensions beyond these 3, in order for their mathematics to work out consistently. Sometimes 6 extra dimensions, sometimes 7. These extra dimensions, if they exist, are not like the ones you know. They're curled up, compactified, wrapped around themselves so tightly that you'd never notice them in daily life. The standard image is a garden hose. From a great distance, a garden hose looks like a simple one-dimensional line, a single straight path from one end to the other. But if you get close enough, If you walk right up to it and examine its surface, you see there's a whole second dimension wrapped around it, a small circular dimension that the ant crawling on the hose can move along. The ant can go forward and backward along the length, or it can loop around the circumference. The second dimension is real, but it's small, and from far away it's invisible. Extra dimensions in physics would be like that. Curled up so small, far smaller than an atom, far smaller than a proton, that no instrument has ever been able to resolve them. They'd be everywhere, wrapped around every point in space, but too tiny to see or feel or enter. Other, separate theoretical proposals suggest these extra dimensions might not be tiny at all. They might be large, even infinite, but simply hidden from us because ordinary matter and light are confined to move only along our familiar three dimensions, like ink confined to the surface of a page, unable to move up or down into the third dimension that the page itself exists within. We'd be living on a kind of membrane, a slice of a larger space, and we couldn't leave it. Gravity alone might be free to leak outward into the extra dimensions, spreading its strength across more space than we can access, which would naturally explain why gravity seems so much weaker than the other forces. It's not actually weaker, it's just diluted, spread thin across hidden dimensions that we can't see. No experiment has yet found direct evidence of extra dimensions of any kind, despite dedicated searches at the Large Hadron Collider. Physicists have looked for particular telltale signatures, tiny amounts of missing energy in particle collisions that would suggest something had briefly leaked away into a hidden dimension, carrying energy with it that the detectors couldn't account for. Nothing has been found. The idea remains mathematically productive and theoretically taken seriously, and entirely unconfirmed. It may be that extra dimensions exist and we just haven't found the right way to look. It may be that they don't exist, and the theories that require them will need to be rethought. Tonight, both possibilities are still on the table. You can let all of this settle now. These smaller puzzles, these anomalies and theoretical possibilities are not urgent. They're the kind of questions that keep physicists awake at night, or send them back to their equations and their detectors, checking and rechecking, refining and recalibrating, looking for the small signal in the noise. But they don't need to keep you awake. The protons in your body, whether eternal or merely long-lived, are stable enough to hold you together for this night and for every night of your life. The extra dimensions, if they exist, are curled up too small to notice. The muons and axions and neutrons are doing whatever they do, whether we understand them or not, and your breathing continues, slow and steady, unaffected by any of it. Let's turn now to where all of this actually lives, quietly, in the world around you tonight. These aren't distant abstractions confined to research papers, filed away in university libraries, discussed only by people with advanced degrees in windowless rooms. They're woven into the very room you're lying in. They're present in the objects around you, in the light and the silence, in the walls and the air, in your own body. The unsolved problems of physics aren't somewhere else, out there in deep space or buried inside particle accelerators. They're right here, right now, in the dark with you. Consider the phone charging somewhere nearby, or the GPS chip inside it if it's sitting on your nightstand. GPS satellites orbit roughly 20,000 kilometers above the Earth, moving fast enough and experiencing gravity weak enough compared to the surface that Einstein's relativity predicts their onboard clocks tick at a very slightly different rate than clocks on the ground. This isn't a theoretical subtlety, it's a genuinely measurable difference, a real physical effect. And if engineers hadn't corrected for it precisely, hadn't built the relativistic adjustment into the satellite's timing system, GPS positioning would drift, by several kilometers within a single day, by enough to make it completely useless for navigation within about a week. Every time your phone locates you accurately, every time a map application shows your position as a steady blue dot on a street grid, it's quietly relying on a theory that was built, in part, to explain the wobble of Mercury's orbit. That same wobble, that tiny discrepancy of a few dozen arcseconds per century that sent astronomers hunting fruitlessly for an invisible planet named Vulcan for half a century, is the reason your phone knows where you are. Einstein's correction to Newton, the curvature of space and time, the slowing of clocks in motion and in gravity, all of it is baked into the mundane miracle of satellite navigation. Physics that was once a profound mystery, a crack in a supposedly complete system, is now a piece of engineering that fits in your pocket. Consider the light in the room, or the absence of it if you're lying in the dark right now. Every glowing light bulb, every screen, every LED indicator, ultimately depends on quantum mechanics to explain how electrons move through materials, how semiconductors work, how transistors, the tiny switches inside every computer chip and phone processor, turn on and off billions of times per second. A transistor is a device that controls the flow of electrons through a material by manipulating quantum effects, by exploiting the same strange rules that make an electron exist as a spread-out wave of probability until it's measured. The device this narration might be playing from, the phone or speaker or laptop that's producing these words in the dark, is built from billions of transistors, each one a small engineered puzzle that only works because quantum mechanics is true. The same strange quantum uncertainty that fuels the still unsolved measurement problem, the question of what a measurement actually is, and whether the wave function really collapses, is at this very moment running the processor that decodes and plays back this audio. The foundational mystery and the practical application sit side by side, part of the same physics, one aspect well understood and engineered down to the nanometer, the other still debated after 100 years. Consider your own body, not as a metaphor, not as a poetic image, but as a physical fact. The atoms making up your bones, your blood, the neurons quietly firing in your brain as you drift towards sleep, were forged inside the cores of ancient stars. Built up through nuclear fusion, hydrogen fusing into helium, helium into carbon, carbon into oxygen, up through the periodic table, element by element, in the crushing heat and pressure, at the center of stars that lived and died long before the Earth existed. When those stars eventually exhausted their fuel, some of them ended in the enormous explosions called supernovae, scattering their newly forged elements across space. Those atoms drifted for billions of years, caught up in clouds of gas and dust, eventually clumping together under gravity to form a new star, our Sun, and a set of planets around it, one of which became the Earth. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of every organic molecule in your body, all of it is stardust, the literal ash of dead suns. This is not a poetic way of saying that you are connected to the universe. It's a physical description of where the atoms in your body came from, verified by spectroscopy, by nuclear physics, by the measured abundances of elements in stars and in the space between them. But recall something we talked about earlier. Stars, galaxies, and all the ordinary matter that eventually became you, every atom of every element forged in every stellar core, make up only about 5% of everything that exists. The rest, the 95%, is dark matter and dark energy. Dark matter, that invisible mass that holds galaxies together but doesn't interact with light, surrounds you too, tonight, in your room. It's not somewhere else. It's not confined to distant galaxy clusters. It's here, passing through the walls, through the floor, through your body, the same way neutrinos do, or even more quietly. The Earth's gravity holds a halo of dark matter around it, just as it holds the atmosphere, and you are moving through that halo right now, without feeling it, without any instrument in your home being able to detect it. An invisible ocean that outweighs and outnumbers everything visible by a wide margin, still unidentified, still quietly present, filling the space around you and within you, and you would never know it was there, except for the patient work of astronomers, measuring the rotation of galaxies and the bending of light. And dark energy, that unknown repulsive pressure pushing the universe apart, is also here. It's a property of space itself, according to the leading explanation, which means it's present in every cubic centimeter of the room you're lying in. It doesn't affect you directly. The expansion it causes only becomes noticeable over vast cosmic distances, between galaxy clusters, not within them, not within a single room. Gravity holds local structures together against the outward push, which is why your body isn't being slowly stretched apart as you lie there. But the dark energy is present. It's a part of the space you occupy, a part of the vacuum, and we don't know what it is. 68% of the universe's total energy budget, right there in the dark with you, nameless and unexplained. Consider the sky above the roof over your head right now, even though you can't see it from where you're lying. The stars you might glimpse through a window if you got up and looked. Those distant points of light, each one is held together against its own gravity by a delicate balance. Gravity wants to crush the star inward, pulling all its mass toward the center. Something has to push back to keep the star from collapsing. For most stars, for most of their lives, that push comes from the energy released by nuclear fusion in the core, a constant outward pressure from the conversion of hydrogen into helium. But for smaller stars, the ones that have exhausted their fuel, or for the dense remnants left behind after larger stars die, the push comes from something stranger. It's called electron degeneracy pressure, and it's a purely quantum mechanical effect. It arises from the Pauli exclusion principle, the rule that two identical particles, like electrons, can't occupy the exact same quantum state. When you try to pack electrons too closely together, they resist, not because of any force between them, but because of the fundamental rules of quantum statistics. This resistance is what holds white dwarfs up against gravity, what keeps them from collapsing further, and it's a direct consequence of the same quantum mechanics that produces the measurement problem and entanglement and superposition. The stars in the sky, even the dead ones, are held together by physics we still don't fully understand at the level of its deepest interpretation. And the nuclear fusion reactions that power the living stars, the ones still burning, depend on another quantum effect. The cores of stars are hot, but they're not hot enough, according to classical physics, for protons to overcome their mutual electric repulsion and fuse together. The temperature in the sun's core is about 15 million degrees, which sounds like a lot, but it's not nearly enough if you just calculate the energy needed to push two positively charged protons close enough for the strong nuclear force to grab them. Fusion happens anyway because of quantum tunneling. Protons don't have to have enough energy to climb over the repulsive barrier. They can tunnel through it, appearing on the other side without ever having been in between, the way an electron can appear in a location it classically couldn't reach. This tunneling is genuinely probabilistic, genuinely unpredictable for any single particle. The rate of fusion in the sun depends on the probability of tunneling, which is set by the same quantum rules that govern everything else. And those rules, as we've discussed, have an interpretation problem at their heart. The sun is shining, right now, on the other side of the Earth, because of a process that relies on the same unresolved physics we talked about earlier. And the distant galaxies, the ones visible only through powerful telescopes, are all rushing away from us a little faster every year. Carried outward by that same unexplained dark energy, a force with no confirmed source, quietly stretching the universe wider while you sleep. The space between galaxies is increasing, and the rate of increase is itself increasing. The expansion that Edwin Hubble first measured in the 1920s, that led to the picture of a universe with a beginning, has turned out to be accelerating, driven by something that wasn't supposed to be there, something Einstein discarded and then the universe insisted on keeping. While you lie in your bed, the large-scale structure of reality is changing, slowly, imperceptibly, in a way that no one can yet explain from first principles. Let's spend some time now with the harder questions, the ones that go beyond specific measurements and puzzles, into genuinely strange, sometimes uncomfortable philosophical territory that physics finds itself brushing up against. These are questions that don't just ask what the universe is made of or how it moves, but why it has the particular properties it does, and whether those properties suggest something about our place in it. One is called the fine-tuning problem. Several of the fundamental constants of nature, numbers like the strength of gravity, the mass of the electron, the strength of the force holding atomic nuclei together, appear, as best physicists can calculate, to sit within an extraordinarily narrow range that allows for a universe capable of forming stable atoms, long-lived stars, and complex chemistry, the kind that eventually allows for life. If gravity were even slightly stronger, stars would burn through their fuel too quickly. The universe would flash and fade, a brief bright burst of massive stars that lived fast and died young, with no time for planets to form, no time for life to emerge. If gravity were slightly weaker, stars might never have ignited at all. Gas clouds would have drifted apart before they could collapse and heat up enough to begin fusion, and the universe would be a cold, diffuse, empty place, with no points of light and no sources of heavy elements. If the strong nuclear force were slightly different, the consequences would be equally profound. Make it a little stronger, and protons and neutrons would bind together so tightly that all the hydrogen in the early universe would have been processed into heavier elements too quickly, leaving no hydrogen to fuel the long, steady burning of stars like our Sun. Make it a little weaker, and atoms heavier than hydrogen might never have formed at all. The universe would be a sea of hydrogen and helium, with no carbon, no oxygen, no chemistry resembling anything we know, no building blocks for anything complex. Nobody currently knows why these constants have the specific values they do. They seem arbitrary. They could, as far as the underlying mathematics is concerned, have been different, but they're not. They're set to the precise values that allow for a universe with stable structures, with stars that burn for billions of years, with planets, with chemistry, with the slow unfolding of complexity that eventually produced life. And nobody has found a deeper physical law from which their values necessarily follow, a theory that would make these numbers inevitable, the way Kepler's ellipses became inevitable once you had Newton's law of gravity, doesn't yet exist. Some physicists suggest an idea called the multiverse, the possibility that our universe is only one among a vast, perhaps infinite number of separate universes, each with different, randomly set physical constants. In most of these universes, the constants would be wrong. Stars wouldn't form, chemistry wouldn't happen, life wouldn't arise. But in a small fraction, the numbers would happen to fall in the narrow range that permits complexity and observers. And we, by definition, find ourselves in one of those rare universes, because only such a universe could produce beings capable of asking the question. This is called the anthropic principle, and it has a certain logical appeal. It doesn't explain why the constants have the values they do in any deep causal sense. It just notes that if they were different, we wouldn't be here to wonder about them. The apparent fine-tuning is a selection effect, not a design. Other physicists find this explanation deeply unsatisfying. A multiverse, by its nature, may be permanently untestable. If these other universes are causally disconnected from ours, if no signal or influence can ever pass between them, then their existence is a matter of pure inference, or pure speculation, with no possible experimental confirmation. That sits uneasily with what many consider one of the core requirements of science, that theories must be testable, that they must make predictions that can be checked against observation. The multiverse may be the correct answer to the fine-tuning problem, or it may be a way of giving up on finding a deeper physical explanation. Tonight, there's no consensus, and the question sits there, at the boundary between physics and philosophy, waiting for someone to find a way to bring it back into the realm of testable science. Another hard question is the black hole information paradox, connected to that same deep tension between quantum mechanics and general relativity we talked about earlier. General relativity predicts that anything falling into a black hole is, for all practical purposes, lost forever behind its event horizon, the boundary beyond which nothing, not even light, can escape. Once you cross that threshold, you are causally disconnected from the outside universe. No signal, no information, no trace of what you were can ever climb back out. You're gone, and everything you carried with you is gone too. But in 1974, the physicist Stephen Hawking showed that this picture isn't quite complete. Using quantum mechanics applied near a black hole's boundary, he demonstrated that black holes should very slowly radiate energy. This is now called Hawking radiation, and it's an effect of quantum processes near the event horizon, particle-antiparticle pairs being pulled apart by the black hole's gravity, one falling in and the other escaping, carrying away a tiny bit of the black hole's mass. Over unimaginably long stretches of time, far longer than the current age of the universe, black holes should eventually evaporate away completely, shrinking and shrinking until they vanish, leaving nothing behind but the radiation they emitted over their lifetime. Here's the paradox. Quantum mechanics has a deep, foundational rule, stating that information can never truly be destroyed. In principle, if you knew everything about a final state precisely enough, you could always mathematically reconstruct everything about how it got there. The equations of quantum mechanics are reversible, information is conserved, but Hawking radiation, as originally calculated, appears to come out completely random, carrying no trace of the specific information about whatever fell into the black hole in the first place. A black hole formed from a collapsing star full of particular elements and particular structures, which then spent billions of years swallowing whatever happened to fall in, eventually evaporates into a featureless, random bath of thermal radiation. All the information about what went in, the specific details, the unique history, seems to be gone. When a black hole finally evaporates away entirely, leaving nothing behind but this apparently random radiation, does all the information that fell in over its lifetime simply vanish from the universe, violating one of quantum mechanics' most fundamental rules? Or is that information somehow smuggled out, subtly encoded in patterns within the radiation, patterns too complex for us to have decoded yet? This question has occupied some of the most capable theoretical physicists alive for decades. In recent years, there's been progress, hints that information might be preserved after all, encoded in the intricate structure of space itself, near a black hole's boundary, perhaps in the quantum entanglement between the radiation and the black hole, or in subtle correlations in the emitted particles that would take an impossibly long time to measure, but are there in principle. But a fully agreed-upon resolution tonight still doesn't exist. The paradox stands as one of the sharpest points of contact between the two great theories, a place where they can't both be right without some deeper principle reconciling them. There's also the question of what happened before the Big Bang, or whether that question even means anything at all. General relativity, run backward in time, predicts the universe emerged from a single point of infinite density and temperature, called a singularity. At the singularity, the mathematics breaks down. The equations produce infinities, the same way the old ultraviolet catastrophe did. And most physicists suspect, as they suspected then, that this prediction of infinity is itself a signal that the theory is being pushed past its valid limits. The singularity is not a literal description of what happened. It's a placeholder for physics we don't yet understand, physics that would require a working theory of quantum gravity to describe. Some theories propose the universe experienced a rapid period of expansion called inflation in its earliest moments, smoothing out and stretching whatever came before into something unrecognizable, meaning the true beginning might have looked nothing like a single point at all. Other, more speculative ideas propose a cyclical universe, expanding and eventually contracting and bouncing back into a new expansion, over and over, without any true singular beginning ever occurring. None of these ideas currently has strong experimental confirmation, and it's entirely possible that the true nature of the universe's beginning, or whether it's even meaningful to ask what came before time itself existed, may remain forever outside the reach of any experiment we know how to design. The question hangs there, at the edge of what physics can currently address, as open tonight as it has ever been. There's one last open question worth sitting with, one that connects physics to a much older, more personal kind of wondering, the kind you might have had as a child looking up at a clear night sky, before you knew any of the technical names for things, before you'd heard of dark matter or quantum mechanics or the expansion of the universe. Just the simple, quiet question that rises up when you're lying in the dark and the stars are out, and the world is very still, is anyone else out there? This question has a name in the language of physics. It's usually called the Fermi paradox, named after the physicist Enrico Fermi, who is said to have raised it casually over lunch with colleagues in 1950 during a conversation about the likelihood of intelligent life elsewhere in the galaxy. The story goes that Fermi listened to the discussion for a while, the back and forth about the odds and the distances and the timescales, and then he asked a question that cut through all of it. Well, where is everybody? It's a simple question, and it has never been answered. The numbers on their face seem to make the absence of contact hard to explain. The observable universe contains something like 2 trillion galaxies, not 2,000, not 2 million, 2 trillion. Each of those galaxies, on average, contains hundreds of billions of stars. The total number of stars in the visible universe is a number so large it loses meaning, somewhere around 1 trillion, a 1 followed by 21 zeros, and around many of those stars we now know there are planets. The science of detecting planets around other stars has advanced rapidly in the past few decades, and what it's found is that planets are common, not rare. They're the rule, not the exception. Most stars seem to have them. Some have several, whole families of worlds orbiting at different distances, some rocky like Earth, some gaseous like Jupiter, some in between. The raw ingredients for life as we know it, carbon, water, energy from a stable star, are scattered generously throughout the cosmos, not concentrated in one special place. Water is everywhere. Organic molecules are everywhere. The conditions that allowed life to emerge on Earth don't seem to be unique or even particularly unusual. Given the sheer scale of time and space involved, billions of years, billions of worlds, it seems statistically reasonable, almost inevitable, that intelligent, technological life should have arisen many times over. Not just simple microbes huddled around deep-sea vents, but civilizations, beings that build things, that send signals, that leave traces. And the universe is old, far older than the Earth, far older than the Sun. The Milky Way galaxy alone is about 13 billion years old. Our Sun and its planets formed about 4.5 billion years ago. Life on Earth began within a few 100 million years after that, as soon as the surface cooled enough to allow liquid water. Complex life took much longer, a few billion years. Technological civilization, the kind that can send and receive signals across interstellar distances, has existed on Earth for about a century. A single century out of 4.5 billion years, a blink of an eye. But if another civilization had arisen even a few million years earlier than ours, a tiny fraction of the galaxy's lifespan, and had developed technology at roughly our pace, it would have had millions of years to spread, to build, to broadcast its presence across the stars. A few million years is nothing in cosmic time. The dinosaurs went extinct 65 million years ago. If a civilization had arisen on a planet orbiting a star just a few million years older than our Sun and had followed a roughly similar trajectory, it should have had more than enough time to become detectable, to fill its galaxy with signals, or with artifacts, or with visible engineering on a scale we could notice. The galaxy should, by this logic, be teeming with evidence of intelligent life. And yet, despite decades of careful listening with radio telescopes and careful looking with increasingly powerful instruments across many wavelengths of light, we have found, tonight, no confirmed signal, no confirmed signature, no artifact, no beacon, no sign of deliberate communication or even of unintentional leakage, the kind of radio and television signals that our own civilization has been spilling into space for the better part of 100 years. Nothing, just silence. This gap between how likely intelligent life seems on paper and how empty the sky actually appears is the paradox. It's not a paradox in the sense of a logical contradiction. It's a paradox in the sense of a deep tension between two things that both seem true but can't easily be reconciled. On one hand, the universe appears to provide abundant opportunities for life to arise. On the other hand, we see no evidence that it ever has, not beyond our own single planet. There are many proposed explanations, and none of them are fully satisfying, which is why the question remains open tonight. Some explanations focus on the first part of the tension, the apparent abundance of opportunity. Maybe intelligent life is far rarer than the simple math suggests. Maybe the chain of events that leads from simple self-replicating molecules to complex multicellular organisms, to tool-using, language-speaking, technology-building beings, is far more improbable than we realize. Maybe there's some great filter, some step along that chain that almost never happens, and we've somehow made it through. The emergence of life itself might be the filter, an event so unlikely that it happened exactly once in the history of the galaxy. Or the emergence of complex cells, the kind with nuclei and organelles, which happened on Earth only once in roughly 2 billion years of microbial existence, might be the bottleneck. Or the development of intelligence of the particular kind of brain that can do abstract reasoning and accumulate knowledge across generations might be a fluke, not an inevitable outcome of evolution. If any of these steps is staggeringly improbable, then we might be alone, or nearly alone, and the silence is simply the silence of an empty galaxy. Other explanations accept that intelligent life might be common but focus on the difficulty of detecting it. Maybe civilizations don't broadcast for very long. We've been sending detectable radio signals into space for about a century, and we're already getting quieter, switching to fiber optics and digital encoding that leak less into the void. Maybe the window of detectability is short, a few centuries at most, and the odds of two civilizations overlapping in time and being close enough to hear each other are much smaller than the raw number of civilizations would suggest. Maybe advanced civilizations communicate in ways we can't detect yet, using physics we haven't discovered, signals that pass through our instruments unnoticed because we don't know what to look for. Maybe they're not using electromagnetic signals at all. Maybe they're using modulated neutrinos or gravitational waves or something entirely outside our current understanding. Some explanations are darker. Maybe technological civilizations tend to destroy themselves. We've only had the capacity for global self-destruction for about 80 years, since the development of nuclear weapons, and we've come close to using them more than once. We're now facing other global threats, climate change, ecosystem collapse, pandemics, that could destabilize civilization without a single bomb being dropped. Maybe this is normal. Maybe every civilization that reaches a certain level of technological power eventually faces a set of challenges: resource depletion, environmental damage, weapons of mass destruction, that it has a high probability of failing to navigate. The silence might be a graveyard, not an empty wilderness. Or maybe the silence is deliberate. Maybe advanced civilizations, for reasons we can't guess, choose to stay hidden. Maybe there's something out there that they're hiding from. Maybe they're watching, waiting for us to reach a certain threshold of maturity or stability before making contact. Maybe they have ethical rules about not interfering with less advanced civilizations, the way we have rules about not interfering with uncontacted tribes in remote parts of our own world. The universe could be full of quiet observers, and we're just not ready to join the conversation. Or maybe the distances and timescales are simply too vast. The nearest star to our sun is 4 light-years away. The nearest galaxy of any significant size is 2.5 million light-years away. Even if the galaxy contained thousands of civilizations, the average distance between them might be hundreds or thousands of light-years. A signal sent from one to another would take centuries to arrive. A conversation, a simple exchange of hello and hello back, would take longer than the entire lifespan of most human civilizations. What would be the point? Maybe every civilization that arises eventually looks out at the stars, does the same math, and reaches the same quiet conclusion: the universe is too big for company. The Fermi paradox isn't strictly a physics problem the way quantum gravity is, or the way dark matter is. It doesn't arise from a contradiction in our fundamental equations or a measurement that refuses to match a prediction, but it grows directly out of physics, out of how large the universe actually is, and how old, and how much matter it contains, and how the laws of nature seem to allow for the emergence of complexity and life. It's a question that sits at the intersection of physics and biology and philosophy, and it remains, tonight, wide open. The silence from the sky is as complete now as it was when Enrico Fermi first asked where everybody was, more than 70 years ago. If you were to hold all of tonight in one single image, all the history, and all the puzzles, and all the open questions, it would be this. A very old, very careful, very human project, stretching back to Babylonian astronomers lying beneath the stars with clay tablets, writing down the positions of the wandering lights, generation after generation, building the first dataset without knowing what it would become. Through Greek philosophers insisting that the world had reasons rather than moods, that lightning was not the anger of Zeus, that nature could be understood by human minds. Through Newton alone, in a quiet house during a plague, working out the laws of motion and gravity that would explain the fall of an apple and the orbit of the moon with the same simple mathematics. Through Einstein rewriting space and time from a patent office, showing that gravity is geometry, that clocks slow down and rulers shorten, that the universe is stranger and more fluid than anyone had guessed. Through generations of physicists building instruments buried deep underground and rings of magnets miles wide, waiting patiently in the dark for a single neutrino to interact, for a single dark matter particle to bump into an atom, for a single proton to decay after a span of time longer than the current age of the universe. All of them chasing the same basic, patient question: what is actually going on here, underneath everything? And what that project has found, again and again, across centuries, is a strange and honest pattern. Every time human understanding felt complete, truly complete, a small crack appeared. A stubborn wobble in Mercury's orbit that Newton's gravity couldn't explain. An impossible glow predicted at ultraviolet wavelengths that the old physics insisted should be there, but that real objects didn't produce. A whisper of extra gravity holding galaxies together that shouldn't be there. A light too dim, a proton too small, a wobble in a muon's spin too large. Each crack, eventually, opened into something larger and truer than what came before. Newton's gravity gave way to Einstein's curved space. The ultraviolet catastrophe gave way to quantum mechanics. The missing mass in galaxy clusters gave way to the whole mystery of dark matter. And each time, the new understanding didn't simply replace the old one. It contained it, preserved it as a special case, an approximation that still worked in the domain where it had always worked, but that was no longer the final story. Dark matter, dark energy, the arrow of time, the measurement problem, the tension between gravity and the quantum world, the imbalance between matter and antimatter, the silence from the stars. These aren't failures of physics. They're not signs that the whole enterprise has gone wrong, or that we're somehow worse at understanding the universe than our predecessors were. They're the visible edges of the map, the places where careful people have gotten honest enough and precise enough to notice exactly where their current understanding runs out. That's not a small achievement. Knowing precisely what you don't know, down to the decimal point, is one of the hardest and rarest things a mind can do. It's far easier to pretend you have a complete picture, to smooth over the gaps, to add another epicycle, and declare the model finished. It takes a different kind of discipline to point at the gap and say, this is where the map ends. We don't know what's beyond it yet, but we're working on it, and here's exactly how large the gap is, exactly what measurements don't match, exactly which predictions are coming out wrong. That kind of honesty, that willingness to live with open questions rather than close them prematurely, took thousands of years of watching the sky, and dropping objects, and building magnets, and being willing to be wrong to develop. The neutrinos are still passing through you, right now, as they have been this entire time, completely unaffected by anything you've heard tonight, unaffected by the walls of your room, unaffected by your own body, by your bones and blood and the quiet thoughts drifting through your mind. On their way from the center of the sun to somewhere on the other side of the earth beneath you, straight through the mattress, straight through the floor, straight through solid rock, as if none of it were there at all. Trillions of them, every second, tiny and nearly massless and barely interacting with anything, carrying with them questions about their own nature that physicists still can't answer. What is their exact mass? Why are they so light? Are they their own antiparticles? The questions are specific and technical and still wide open, and the neutrinos don't care. They just keep streaming through, silent and invisible, part of the background of being alive on a planet orbiting a star. In a few hours, roughly the same amount of ordinary matter that makes up your body will still be held loosely together against gravity's constant pull, the same way it always is. By electromagnetic forces between atoms, by the strong nuclear force holding nuclei together, by the weak nuclear force governing slow decays, by the shape of space itself curving under your mass, an amount of curvature so tiny it would be impossible to measure, but there nonetheless. Forces still not fully mapped out, in a universe still expanding a little faster with each passing year, pushed outward by something no one has managed to name properly yet, something that makes up more than 2/3 of everything that exists. The dark energy is there, in the room with you, in the space between your body and the ceiling, doing whatever it does, unexplained and undiminished. The dark matter is there too, invisible and gravitationally present, part of the hidden scaffolding that holds the galaxy together. None of that needs your attention tonight. It was happening before you started listening, and it'll keep happening exactly the same way whether you're awake for the rest of this or not. The open questions of physics have been open for decades, some of them for a century, some of them arguably since Babylon, since the first astronomer looked up at the wandering lights and admitted to not knowing what they were. They can wait a little longer. They're not going anywhere, and neither is any of this, if you want to come back to it another night. For now, there's nothing left to figure out, nothing left to hold on to, just this room, this bed, this slow settling weight of your own body sinking a little further into rest. Your body, made of atoms forged in ancient stars, held together by forces that operate at every scale, from the subatomic to the cosmic, still curved gently by gravity's pull, that same old force Newton once traced from a falling apple all the way out to the edges of the visible universe. The same force Einstein reimagined as the shape of space and time, the dip in the mattress, the curve that guides the planets in their ellipses and holds you gently against the sheets, quietly, patiently, holding you exactly where you are.